So we're at the point now, we're ready for acids and bases, and that's going to be chapter 14 and 15. Chapter 14 just says acids and bases, and chapter 15 claims equilibrium, but chapter 14 has a lot of equilibrium techniques and descriptions in it. So really, the authors probably should have put both of them in the same chapter. But we're going to cover them both today. And hopefully I can get finished. If I may run over and spill over into the lab tutorial time. So let me share chapter 14. Let's see, here it is, PowerPoint. And let's make a slideshow out of it. There we go. Okay, now I'm going to move some of this stuff up out of the way. And there he is. It's still connecting. There we go. Okay, everybody's here that was here when I crashed the system. So my apologies. But we do have our, the resolution is back, and that's what I was wanting. Okay, chapter 14, acids and bases. There are several concepts concerning acids and bases that have been developed over the years. One of the first useful definitions of acid bases was published by I think he was Swedish. His name was Arrhenius. And his idea was that acids were any compound that when dissolved in water produced hydrogen ions. So that means that and that's our generic acid. It's preceded with a hydrogen. And of course, you know that some acids can have 2 or 3 of these, right? But we're just going to use one for this discussion. So the compound would have to have a dissociable hydrogen ion in its makeup, so that when it goes into solution, it breaks apart into a proton, which is basically a hydrogen ion, and what's left over. That was Arrhenius' definition of acid. His definition of a base was similar in that the compound had to have a hydroxyl group in its makeup, so that when it goes into solution, it produces this sort of arrangement. Okay, that was Arrhenius' definition, and for most acids and bases, that definition still holds. It's still valid. For instance, sodium hydroxide, or lye, the stuff you pour down your drain when you want to clean it, is a base. And it's a base by Arrhenius' definition. It has a hydroxyl group in it, which it dissociates when it goes into solution. The problem with that definition arose when bases were identified that did not have hydroxyls in their makeup, but they still produced basic solutions. In other words, they had hydroxyls in solution, and where'd they come from? For instance, when we put ammonia in solution, right, what you end up with is the ammonium ion plus a hydroxyl. right? So where did it come from? It came from that water molecule. This ammonia stripped the proton off of that ammonia, off of that water molecule, and what it left behind was a hydroxyl group. So Arrhenius definition doesn't work for that base. So Bronsted and Lowry independently, that's why they're both given credit for it, devised a solution to this problem. Their definition focused only on protons. So what they said was that an acid was a proton donor. And that still holds for the Arrhenius type of acid. But a Bronsted-Lowry base is any compound, when you put it in solution, accepts a proton. So they just completely ignored the hydroxyl and focused on the protons. The value of the Bronsted-Lowry definition is not just to solve this problem, but now you can have acid-base definitions for non-aqueous solutions. So if the solvent is not water, but you can still transfer a proton, then you have an acid-base reaction. Excuse me. All right. So what we have, let's see. I think I'll stick to the slides for now. So for both definitions, hydrochloric acid in solution reacts with water and transfers a proton. The acid is the proton donor, and that makes water the base, the proton acceptor. And this is what happens with strong acids. When they go into solution, in aqueous solution, they transfer the proton to water, and you get this special ion here called a hydronium ion. And in fact, even though we write reactions that show protons as separate units, for instance, we would say something like this. And all that's in aqueous solution. If we write it like that, the stoichiometry is still valid. It works with that. But in reality, that never happens. Protons never exist as separate hydrogen ions like that. They're always combined with something. They transfer only. So that's why this is the valid form, the hydronium ion in aqueous solution. So you need a water there, and that would attach itself to the water molecule. But we still write them this way, right? And we're going to do that. We're going to just continue to write them like this. I just want you to understand that in reality, in the real world, that never happens. That's a convenience for writing acid-base reactions. Okay. So the Bronsted-Lowry acid-base theory says that their model says that protons are transferred, and the transfer of the proton determines which is the acid and which is the base. Now, we already know from previous chapters and studies that the strength of an acid depends on how, well, actually, the dissociation or the breaking of a bond depends on several factors, and acids are no different. Right, so what happens to that proton? This is the water molecule, this is the ammonia molecule, and there's a tug of war going on between the water and the ammonia. And the strength of that tug determines how many of these protons will be transferred to ammonia molecules. As a matter of fact, ammonia is a weak base, which means it does not attract protons strongly. All right, so in solution, you'll find that most of the ammonia is in this form. And very little of it is in this form. 98% of it will be that form. So it doesn't extract a proton very efficiently from water. It still makes a base, but because of that weakness of the pull on the proton, we call it a weak base. It does not completely become protonated. Okay, water molecules do the same thing, right? You get two water molecules in close proximity, there will be a tug of war between two water molecules and the transfer of a proton. Okay, so what does that look like? That reaction looks like this. And of course, that's a liquid, and that's a liquid. And if you transfer a proton, if the transfer is successful, then you'll have a proton transferred over here to make the hydronium, and you'll have a hydroxyl left behind. And now this is considered aqueous. Okay, so that reaction does occur in water, in pure deionized distilled water. That reaction occurs, but it doesn't occur to a very great extent. Right? In terms of the equilibrium expression, right? If these are both liquid, of course, they're not part of the expression. So if we write a K value for that, we have just this one and that one. Okay? And the K value for that is very small. 10 to the minus 14. Right, so you don't get a lot of this in an equilibrium pure water situation. But it does occur. It always occurs. No matter what else you put in water, that reaction always occurs. It's just that if you put something in water that has a much larger equilibrium coefficient, equilibrium constant, then it will dominate the reaction environment. But make no mistake, that reaction always occurs in aqueous solution. Okay, so we have some definitions that we need to consider. Let's just use this one. Okay, so if this one is the one that receives the proton, right? If this one goes from here to here, this one receives the proton. It means it's a base. So this would be the base. And this would be the acid. Okay, I know this is kind of weird. You know, which one's which? Well, at the time of the reaction, one becomes the base, one becomes the acid. Well, we produce this one, that one becomes this. So now this one becomes an acid. It can donate that proton. So now this is, rather than call it just another acid, it's related to this one as the conjugate acid of that base. That means that this one is the conjugate base of that acid. Now in our slide, they've actually used an acid, well, a generic acid, put it in solution, and it transfers a proton over to the water. That means the acid is here, water becomes the base, and we produce a conjugate acid, the hydronium ion, and a conjugate base, the anion of the acid, whatever's left over. Okay, that's just definition, so that we can tell them apart. Okay, what do we mean by a strong acid, weak acid? In chemical terms, a strong acid is any compound at equilibrium where the dissociation of the acid, transfer of the proton, gives you predominantly right side of the equation. Like this would dominate, which is another way of saying that the acid dissociates. Essentially, completely dissociates. Okay, that's in chemical terms. We normally think of, I mean, our intuition is that a strong acid is anything that will burn your hand, right? If it's an acid and it burns your hand, you think it's a strong acid. Well, in fact, weak acids can do that. All you need is enough hydronium ions in that solution to attack your skin. If the concentration is high enough, then even a weak acid will cause damage. So in chemical terms, we mean by a weak acid is one in which the equilibrium lies to the left, right? There's incomplete dissociation, very little dissociation. So the equilibrium constant will be much, much less than 1. That's a weak acid. And when we talk about corrosive properties of acids, a weak acid can be corrosive. All you need is a high enough concentration. And that looks back to the concept of equilibrium constant versus equilibrium position. An equilibrium position, which has a very high concentration of a weak acid, will produce sufficient numbers of hydronium ions to damage your skin. Okay, so something like acetic acid, vinegar. 5% solution is normally what is marketed as vinegar, and it produces a sour taste, but it doesn't damage your tongue, or doesn't eat the inside of your mouth off and spill it on your hand, and it doesn't do any damage. But we used to use in the laboratory, we could buy it in 5-liter bottles, glacial acetic acid, which is another word for 100% acetic acid. It was extremely corrosive and dangerous to handle. On top of that, it's an organic compound, right? Just to comment on safety. Acetic acid, right? There's your organic component. If you get that organic molecule in the vicinity of an oxidizing agent like nitric acid or sulfuric acid, then they will react violently. And that's why you don't store, even though this is an acid and nitric acid is an acid, you don't store them together, right? Because they can react. Okay, back to our topic. So the chemical definition has to do with equilibrium. Strong acids equilibrium lies far to the right, and what we mean by that is it dissociates completely or nearly completely. Weak acids do not. Their equilibrium lies to the left with the undissociated molecule. And this is just the author's idea of explaining that. And here we've compiled everything together your textbook did this. Put everything together in a table to say, and that K value, remember when we first introduced the concept of equilibrium, K's with a subscript, some of them have special meanings. So Ka is the acid dissociation constant, equilibrium constant for any particular acid. If the Ka is very large, you have a strong acid. It's very small, you have a weak acid, so forth and so on. Now, the other concept is, what does that mean in terms of the conjugate base? Right? If you have an acid that reacts with water and with equilibrium, and you have the hydronium produced, right? So here's the acid, here's the base, here's the conjugate acid of that base, and here's the conjugate base of that acid. If this is a strong acid, that means it wants to give up its proton. I mean, it really wants to get rid of that proton, which means the conjugate base is weak. If this is strong, the conjugate base is weak. In other words, it doesn't want a proton. Proton acceptor is a base. It doesn't want a proton. It's a weak base. Whereas this is a strong acid. Vice versa. If this is a weak acid, it wants to hold on to that proton. So any conjugate base that it produces is going to be strong. It wants a proton desperately. And if you just put this part of the molecule separately into water, right? Not this one, but that one. Say you make a salt of it, like sodium, like that. Put that into solution, then it completely dissociates. Remember, all sodium salts are soluble. It makes that in solution. Now it's looking for protons, right? It was derived from a weak acid, so that makes it a strong base, and it's on the lookout for protons. Well, if it's in aqueous solution, it's going to strip them off of water molecules. Right? It's going to take a proton off of that to make this acid, and what does that leave behind? Right? If it takes that away, you got this hydroxyl. Okay? So that if you put just that in solution, not as the acid, but as the salt, then you get a basic solution because it's a strong base, strips a proton from water and leaves a hydroxyl behind. Okay, so that concept, strong acids, weak conjugate base, weak acids, strong conjugate base. That reaction I showed you earlier where two water molecules reacted, the generic term for all of those types of reactions are autoionization or self-ionization. It happens not just with water, but it happens with ammonia. Any pure acid or base will do that. Autoionization. Water has a special name for it. It's called, well, that makes water amphoteric, which just means water can behave as an acid or a base. Ampho means both ways. It goes both ways. And I gave you the equilibrium constant, and Kw is special for water. The equilibrium constant, Kw, whenever you see Kw, it always means equilibrium constant for water. And at 25 degrees centigrade, that value is 1 times 10 to the minus 14. Okay, and notice here we've written it as proton and hydroxyl, right? We know that that proton is really a hydronium. but the stoichiometry, the equilibrium, works either way. And it's more convenient just to write the proton, right? So I just wanted to make that point. In reality, it's a hydronium, but for our purposes and for calculation purposes, it's easier to write it as a proton. Okay, so suppose you have a solution and the concentration of hydrogen ions or protons is equal to the concentration of hydroxyls. You have a neutral solution. That's what happens when you react water with water and you get that reaction, right? Where did these come from? They came from here, right? There's a one-to-one relationship, right? So if you react one of these and one of those, you get one of these and one of these. So they're equal concentration. Under that situation, that's the only time, well, not the only time, you can make it happen with buffers, but we'll talk about that later. But if it's pure water, then these concentrations are equal. That means pure water is neutral. That's our anchor point. Pure water is a neutral solution because hydrogen ions, hydroxyl ions are equal in concentration. Now, what is that concentration? Might as well talk about it while we're here. Well, if the Kw is equal to, right, now I'm going to write this as a proton, and that's 10 to the minus 14, and these are equal. What does that mean for each one? Each one of these has to be 10 to the minus 7. That's the only way it can happen in pure water. They have to be equal. So in order to get this times that to equal that, 10 to the minus 7 is it. So in a neutral solution, the concentration of hydrogen ions is 10 to the minus 7th molar, and the hydroxyls is 10 to the minus 7th molar. Right? If we change that ratio, then you get either acid or basic solution. Right? So if the hydrogen ions are greater than the hydroxyls in concentration, you get an acidic solution. I mean, that's just intuitive. You got more protons, you got an acid. What does that mean quantitatively? That means that this would be, let's just pick one. Say 10 to the minus 6th, right? That's a bigger number than this one, isn't it? 10 to the minus 6 is bigger than 10 to the minus 7th. Okay. So if this reaction always occurs, then what does that one have to be? 10 to the minus 8. Minus 6, minus 8 together, minus 14. Okay? If we went the other direction, say this was 10 to the minus 6th, right? You'd have more hydroxyls, it'd be a basic solution, and then hydrogen ions would be 10 to the minus 8. Okay. So what's the equilibrium constant expression for this acid? Well, it depends. If you have an acid-base reaction, or if you have an acid dissociation reaction, in this case, then this one is a valid term in your expression. That one's a valid, and that one's valid. They're all aqueous. We leave the water out, right, because it's a pure liquid. Right? So the expression would look like this. Hydrogen ions, the conjugate base, the conjugate acid, the conjugate base in the numerator, and the undissociated acid in the denominator. That would be the Ka for this generic acid. All right. So if the equilibrium lies to the right, the value of Ka would be greater than 1, a lot greater than 1. If the equilibrium lies to the left for a weak acid, then the Ka would be small, less than 1. Okay. So let's see. We've got this generic acid dissociating. Let's compare the equilibrium of this acid with water, because we know that the water reaction, the self-ionization of water reaction, always occurs in solution. So if water is a better base than A minus, what does that mean? Before we finish this question, just say, what does that first phrase mean? If water is a better base, that means it attracts protons more strongly than A minus. Right? So it attracts protons very strongly. That means that the reaction would definitely be to the right. The products would dominate. Okay? If it was the other way around, if A minus were a better base than water, then this would strip protons from any source it could and drive the reaction to the left. That means that this is a weak acid that's a strong base, in excess of what water would contribute to the reaction. And I just answered this question. Does this mean HA is a strong or a weak acid? Well, it would have to be a strong acid. How about the value for Ka? The Ka would be much greater than 1. Those two are like synonymous. If it's a strong acid, Ka has to be greater than 1. Okay. So, right, just review, what are some strong acids and strong acids, strong bases? Generally speaking, all of the halogens make strong acids, except fluorine. Fluorine is a weak acid, and I'll explain that later. But hydrochloric acid, hydrobromic acid, hydriodic acid, they're all strong acids. Let's see. Strong bases. Alkali metals, the hydroxides of alkali metals are strong bases. Lithium hydroxide, sodium hydroxide, potassium hydroxide, even rubidium hydroxide. They're all strong bases. That means they dissociate completely, almost completely. You'll also see magnesium hydroxide, calcium hydroxide as strong bases. The problem with that concept is they're not very soluble, right? So they don't have the opportunity to dissociate. But the parts of the magnesium hydroxide molecule, the numbers of hydroxide molecules of both calcium or magnesium, once they get into solution, they completely dissociate. So in chemical terms, they are strong bases. All right, so let's get back to this slide. Let's see if we can put these in order of strongest to weakest base. All right, so when we got 3 like that, what I like to do is say, all right, what's the strongest, what's the weakest? And then the other one just fits in the middle. Okay, consider the source. Chloride ion. What's its source? Comes from a strong acid. So that makes chloride a weak base. So chloride would be over there. It's the weakest base of that group. A minus from a weak acid. That makes it a strong base. that means water's in the middle. Okay, that was a fairly easy one to do. Okay. All right. So I think I've introduced this topic a little earlier, stream of consciousness. Sodium A, right? The generic conjugate base of the acid HA, only now it's introduced in solution associated with sodium. Right? So what do you get in solution? Well, sodium is a spectator. It doesn't react with anything, not as the pre-existing ion. But the A minus, if it is derived from a weak acid, okay, that's important, like sodium chloride. The chloride ion would be derived from a strong acid, right? So it would have a certain characteristic. But if A was derived from a weak acid, that makes A minus a strong base. For instance, the acetate ion. Right? That would be a strong base because it's derived from acetic acid, which is a weak acid. Okay, just to prove it, if we had this here, right, the Ka for that is in the neighborhood of 10 to the minus 7. Right? So it's a weak acid, makes a strong base. Okay, so now back to the question. If A minus is the anion of weak acid, that makes A minus a very strong base. So now if you put just that in solution, it's going to go looking for protons. And if water is the only available source, it's going to strip protons from water. And the reaction now is going to be driven to the right. Because A minus is a strong base, it wants to extract a proton from water very strongly. It wants to be on the right-hand side. So the equilibrium expression then for this reaction would shift the equilibrium to the right. That's wrong. The original slide from the publishers said it was to the left, and they were wrong. It's to the right. Now, if, excuse me, if HA were a strong acid, then A minus would be a weak base. Then the reaction would favor equilibrium to the left. A minus would want to stay the way it is. Doesn't want a proton. And then the answer here would be correct. It would lie to the left. But as stated, the equilibrium lies to the right. Okay. Now, with that same reaction, same conditions, weak acid HA, is the value for Kb greater than or less than 1? Well, the Kb is going to be greater than 1. But what does the Kb look like? Right? We've written the equilibrium expression for acid. Let's write one for a base. Right? So rather than use the generic, let's use a real one. Like let's put acetate ion in solution and write the Kb for that one. So we have, let's see, use a fresh marker. Okay, like this. And then that would produce this. Okay, and all of that's aqueous except for water, it's liquid. Right? So the Kb expression then would be this term and the hydroxyl divided by this term. Okay, that would be a Kb expression. Notice that it's not just the reciprocal of the Ka. Right? This is a completely different reaction. So you can't just take the Ka and flip it over and say that's the Kb. It doesn't work that way. This is the Kb expression for acetate ion introduced into aqueous solution. Okay? And this value would be greater than 1 because that's a strong base now. Derived from a weak acid, it's a strong base. The reaction is to the right. Okay? And that's wrong. Okay. Does this mean A- is a strong or a weak base? Well, based on that conclusion, A- would be a strong base. If the reaction is driven to the right, then it has to be a strong base. All right. All right, so with this information, we're told that acetic acid and HCN, which is what? Right, there's no oxygen there, so we start with hydro. Hydrocyanic. This is the cyanide ion, polyatomic, and ides become X. Hydrocyanic acid. They're both weak acids, but they don't have the same K value. They don't have the same Ka. Acetic acid is a stronger acid than HCN. All right. I don't think I like the blue. Let me get a fresh black one. So we got these two to consider. Yeah, that was not behaving either. Whoa. Marks my hand pretty good. There we go. I could just have to get it started. There's the hydrocyanic, and there's the acetic acid. Okay. Acetic acid is a stronger acid than HCN. So the Ka for this one, HCN, and the Ka for this one, are different. And if this one's stronger, that means this one is greater than this one. Okay? I'm just establishing the given information. Now what they want us to do is arrange these bases from weakest to strongest. Okay? So we know from this arrangement, if this is a stronger acid than that one, then the conjugate base is going to be stronger for this one than for that one. So the conjugate base, we're going from weakest to strongest. So this one is going to be stronger than that one. Okay? Then where do we put the other two? The chloride ion, what is its source? The chloride ion comes from HCl, which is a strong acid, which makes Cl a very weak base. So it's going to be over here somewhere. We just have to figure out where does water go. Well, water, we have to sort of reason this one out. Water is going to be acting as a base. It has a, well, the equilibrium constant is 10 to the minus 14. Right? So I already told you this one's 10 to the minus 7. And that means that water is a very weak acid, which means it would make a very strong base, which would be stronger than this one, actually. But I don't believe it's stronger than this one. So I think what we do is we move this one over. And put water in the middle. I think that's the way it goes. All right. Oh, they're going to give us some more information. All right. So with this information, now we can identify which one's which. The Kw for water is 10 to the minus 14th. The Ka for acetate is 10 to the minus 5th. HCl is a strong acid. HCN is the weakest acid at 10 to the minus 10th. But it's still stronger than water. So that means that water, I put water on the wrong side. Water needs to be over here. Right, water needs to go over there. Based upon these values, let's see, are we going to get some more explanation? No, we're not. Okay, so when we're talking about bases, it would be nice if we could actually calculate the Kb for each of these bases, right? But we haven't got there yet, right? So this is sort of a developing an intuition, right? So these are stronger acids than water. Another weaker acid, excuse me. No, that's not right. If Kw is 10 to the minus 14, that's a weaker acid than any of them. I wonder about that one. The equilibrium says it's this way. Whereas if we introduce these acids, then the equilibrium would be farther to the right. Okay, so that's the correct order. All right, as if that's not confusing enough. Oh man, let's see. This marker is going to be difficult. What about the K for this reaction? Remember, you can write a K for any reaction, as long as you establish the fact that it's capable of equilibrium. So we have this hydrocyanic acid reacting with the fluoride ion, which is what? The conjugate base of HF, and yields the cyanide ion, the conjugate base of HCN, plus the conjugate acid of this base, HF. All right, so what would be the K for this reaction? Is it greater than 1, less than 1, or equal to 1? Well, let's look at the Kas, right, for each one of these. Right? The Ka for HCN says 10 to the minus 10. So it wants to be HCN predominantly. The Ka for HF is 10 to the minus 4. So if we look at it in terms of HF dissociating to go to this side, it has a stronger tendency to want to go to F minus. That's what that would mean. It would tend to go from here to there very strongly. In fact, it would add actually to the equilibrium expression wanting to be reactants, not products. So that means the value would be less than 1, quite a bit less than 1. So if Ka for HCN is very small, that's a strong drive to remain HCN. That's just what I just said, actually. The Ka for HF is small, so it has a strong drive to remain HF. Well, okay. So what's the balance? Right? Which one wins? The Ka for HCN is much, much smaller than the Ka for HF, which means that HCN wins, driving the reaction toward HCN or toward reactants. All right, so that's probably a better explanation than mine for why the Ka is less than 1. Now we're going to calculate Kb. If you know what Ka is, then what's its relationship to Kb? Well, there's your acid dissociation. Right? And that's the Ka that would be assigned to this generic acid. And by the way, whenever we talk about acids and their K values, if there's only one proton that can dissociate, no problem. But if you have multiple protons, it's essential that you understand. Okay. Say there are 3 protons that can dissociate in solution. These reactions in solution always occur in steps. One proton at a time. So each dissociation of a proton has its own Ka. Right? So there would be a Ka1 for that one, and you would take this one and dissociate it, plus another proton. And then you would take this one and dissociate the final proton. Okay? So this one becomes part of that reaction, and this one goes to that reaction. And there are your 3 protons. And each one of these has a K. Okay, I just wanted to make that point before we went any further. So acids like sulfuric that has 2 protons would have 2 K values. Phosphoric acid would have 3 protons. It would have 3 K values. All right. So the associated Kb for this conjugate base would be just the conjugate base added to water, and you get a reaction. Now we write the Kb for that, and that's similar to what I wrote on the board earlier for the acetate ion. Now, how are they related? Right? What if we add these 2 together? Right? What do you get? Right? We can do that because this is a state function, and oh, my mind's gone blank. I'll think of it in a minute. We can add these reactions together to get a target reaction. So what does that do? Well, we cancel the things that are on opposite sides in equal amounts, right? So what do you have left over? Well, you got to cancel that one too. Now what we have left over is water dissociating into hydrogen ions and hydroxyls, right? So that's so what do you do with the K values? Well, when you add 2 equations together, the K's are multiplied. Remember that? Ka times Kb, which is, when you do the multiplication together, this is what you get left over, right? Because that's the dissociation of water. It has to be equal to Kw. So what that means is the Ka times the Kb equals Kw, which is 10 to the minus 14. Okay, so with that knowledge, if you know the Ka, Kw is a constant at 25 degrees. So you just plug in that number. You plug in the value you know here, and you calculate the Kb. Right? So rather than the reciprocal, you have to use this equation to give you either the Ka or the Kb, depending on whichever one you want. So when we are comparing this reaction, break the overall reaction into two competing acid dissociations. Right? So there's one, and there's the other one. Right? That's the HF reaction. This is the hydrocyanic acid reaction. There's the K for this one. There's the K for that one. But the reaction is going the other direction for this one, isn't it? It's going, we need the Kb, right? Because the strength of this one is in terms of how strong a base is it, not how strong an acid is it. So we need to calculate the K for this reaction, right? And there it is, 1.4 times 10 to the minus third is this reaction. Well, actually, that's not Kb. Oh, my apologies. Kb is a value that works in aqueous solution. Right? We used the Kw for aqueous, for pure water, to determine Kb. So this is not Kb. This is actually the inverse. Right? So my apologies. This is the inverse of that reaction. And we can do that based on Hess's law. That's the one I couldn't remember a minute ago. Based on Hess's law, you can add those reactions together, and if necessary, you can flip the K, which we do here, right? So we just invert the K in this case, which is valid for our purposes here. Now we have that K value. Now when we combine the two reactions, which is what we've done here, we have to cancel common terms. Now we have the reaction as originally expressed, and that means that we multiply the K's together. This time we use the inverse of HF, the K value. Multiply them together, and this is the K for the reaction. Okay, 10 to the minus 7. Now this confirms quantitatively what we determined earlier, qualitatively comparing K values for the acids. This actually says the reaction is going to be toward the reactants, 10 to the minus 7. But now we have this value for that reaction. We can do any type of stoichiometry with it we want because we know what the K is. Okay. There was Danish, I think the fellow was Danish. His name was Sorensen. Was working with living systems, and he was interested in the effect of acidity or basicity, as the case may be, on those living cells. But he was finding it unwieldy to use concentrations of hydrogen or hydroxyl ions, right? Because at the levels of concentration, he always had an exponential scientific notation, and it was just unwieldy. So he came up with this system and published it. He did a log transformation, and that's as simple as it is. pH is a log transformation of hydrogen ion concentrations. Right? So what would that be for pure water? Right? Neutral solution. Right? So what he did was he took the log of this. So what's the log of this equals the log, right? Take the log of both sides, the log of this one, right? This is base 10. So logarithms are expressed in terms of the answer to this is what's the power of 10 that equals this number? Well, it's obvious, -7. Well, he didn't like to deal with negative numbers either. So that's why he did this. Negative log of hydrogen ion concentration is equal to 7. So if the concentration is 10 to the -7 molar hydrogen ions, neutral solution, then the pH is 7. And you can do this type of mathematical transformation to any molar concentration and get a p-value, pH. You can do it to hydroxyls too. You say the negative log of the hydroxyl concentration equals what? pOH. Okay? You can even do it to K values. Right? You can do negative log of Kw for water, right? Be negative log of 10 to the -14. So Kw, pKw is equal to 14. All right. It's just a log transformation. That's it. It's nothing special. Well, it's special in how we apply it, but the mathematics is simple. So now this is why neutral solutions are pH 7. So what would an acidic solution be? Well, 10 to the -6. How about that? That would be an acidic solution, right? Well, the negative log of 10 to the -6 is 6, right? So as the solution gets more acidic, the pH value decreases. So values less than 7 are acidic, vice versa. Greater than 7 are basic. And these are some examples, different things. Let's see. Milk is between 6 and 7. There's pure water. Blood is, I think blood is 7.35 to 7.45 is the normal range. If you get outside that range, you get in physiological distress very quickly. That's because blood is a buffered system. We'll talk about buffers in before the day's out. Okay, so normally the pH range doesn't have much value for anything a whole lot less than 1 or much greater than 14. The mathematical calculation can give you negative pH values, but they don't have much meaning. They're not very useful. They can have values greater than 14, but they're not very useful either. It's just that they can happen, but we don't lean toward using those values. They need to be between 0 and 14 to have much meaning. Okay, what's the pH? Calculate the pH for each of the following solutions. Well, this one's easy. 1 times 10 to the minus 4, negative log of that would be 4. Right? How about the pH of this one? This one is a little more complicated. We can calculate the pOH, but we don't know how that relates to pH yet. We'll cover that in just a second. I want to show you the long way around first. So what's 0.04 molar hydroxyl ions? Okay. What did I tell you very early on? That amphoteric reaction, the self-ionization of water, always happens. So we know that Kw equals this, and that's equal to this times this. Okay? So we can say that is that. You have an equation in one unknown now, right there. Divide this one by that one. (10 to the minus 14) and divide it by 0.04. Yeah. So that's 2.5 times 10 to the minus 13. That. Now we just take the negative log of both sides, right? And that gives you pH. So I'll take the negative log of this one, first the log, and then change the sign. So that's 12.6. pH equals 12.6. Okay? That's the long way. I'm going to show you a shortcut in a minute. Oh, by the way, significant figures when we're doing pH calculations. The nature of the log transformation tells us that the number of significant figures in your answer, actually, the number of decimal places in the pH is equal to the number of significant figures in the original number. So this one has 2 significant figures, correct? That means the pH can have 2 decimal places. That's why 12.60 here is derived from 0.040. All right? So, and working backwards, right? How would you work backwards from 12.6 pH to, well, we won't go all the way. We just go back to here. What does pH mean? Well, if this is the negative log, then we need to say the negative log of hydrogen ions is equal to 12.6. Okay? Now, how are we going to find out hydrogen ions from that number? What is the log? What does it mean? Well, if this is base 10, that means this is the power of that. That equals that. But we can't keep that negative out there. Got to get rid of the negative before we can do the transformation. So that means this has to go over there. Now we can use 10 to the minus 12.6 equals hydrogen ion concentrations. Right? And every calculator has 10 to the X on it. You just look for it. It'll be in the neighborhood of the log somewhere. And there's my 10 to the X. So I would just punch 12.6 in and change the sign, make it negative, and then do 10 to the x. And it's 2.5 times 10 to the minus 13 right here. Now, when you do that transformation, of course, this would be 0 here, 0, 0, 0. You look at the number of decimal places, 2 here, that means your answer can have 2 significant figures. So 2.5 is all I can have in my answer. All right. Okay. How about this one? A pH of a solution is 5.85. What's the hydrogen ion concentration? Use that method. Right. There's the expression. Solve for hydrogen ions. Right. And you have to make this one negative, and then that's the power of 10. That equals the hydrogen ion concentration. So plug it into your calculator and prove to yourself that that's correct. All right. Now we're going to relate pH and pOH. This will simplify calculations a lot. All right. So, right, like I said, this KW is always there. That reaction happens all the time. It's always there. So if we take the negative log of the entire equation, which is valid, do the same thing on the left-hand side of the equal sign as you do on the right-hand side, which is a valid mathematical operation. The negative log of KW equals the negative log of this expression, right? And when we do that with logs, if you have a product and you take the log of it, that's the same thing as the log of one term plus the log of the other term. Remember that from algebra? Well, since negative is in front of both of them, that's why negative here and negative there. So now we've got this negative log transformation for each one. So what is that? Well, that's pKW, right? Like I showed you earlier, equals pH, this is pH, plus pOH. So if you know the pOH, if you have calculated the pOH, you just subtract it from the pKW, 14, and you get pH. So that makes that other calculation so much simpler, right? What do we say? 0.04. If we do the pOH of 0.04, 0.04, and change the sign, right, it's negative. Excuse me, it's the log first and then the negative. Excuse me. So we take the log of that and then change the sign, right? 1.3979. Subtract that from 14. I get 12.60. Right? So that was a lot quicker than the other one. I didn't even have to write it on the board. So what's the pOH for each of the following? All right, so if we take this one, we determined the pH earlier to be 4, did we not? So what would be the pOH? 10. Right? 14 minus 4 is 10. And then the pOH of this one, of course, would be 1.40, rounded off. We have to round this one off. Actually, let's see, 2 significant figures. Yeah, 2 significant figures, 2 decimal places. So 1.40 is valid. Okay. If your pH of your solution is this, oh, we're going to go through the calculation. The OH, oh, okay. So to find the OH concentration of a pH 5.85, I would find out what's the pOH first. right? Subtract that from 14. Then you would do the anti-log. That's what 10 to the value of x is, the anti-log. And the anti-log of the difference, 14 minus 5.85 is what? 8.15. And then you do your transformation. Take the anti-log of the negative. Okay. So when we're trying to solve acid-base problems, this is the general scheme that you would want to follow. First, what are the major species? Right? Some species are just spectators. Right? They may be major, and you have to, and we go through the steps, find out what are the major species. Like if we put sodium acetate in solution, the major species would be water, sodium, and the acetate ion. Right? Is sodium going to react with anything? No, just the water and the acetate ion. Then you can eliminate the ones that don't contribute. Then you ask yourself, is this a reaction that, once you've determined the major species and the reactions that are possible, right? There may be more than one reaction possible. Then you say, what type of reaction is it? Does it go to completion? I mean, is it just one of these? Or is it one of these? Okay. That can help you. If it's only this one, then you know that it's just a stoichiometry problem, goes all the way to the other side. But if it's an equilibrium problem, then you need an equilibrium constant and the expression for the equilibrium. With acid-base problems, more often than not, it's convenient to break the problem up into two sections. The first section, go to completion. Even if it's an equilibrium problem, go all the way to the other side. And then, with your ice table, you figure out what are the concentrations. If it goes all the way, then that's your starting point for the ice table equilibrium problem. So we go to completion, then we do equilibrium. And if necessary, solve for the pH. All right, so we need an example, obviously. What about this solution? This is just a first step. If we have a solution of 2 times 10 to the minus third molar hydrochloric acid, what are the major species? Well, what happens to hydrochloric acid in solution? It completely breaks apart, right? So you've got hydrogen ions, chloride ions, and lots of water, right? In aqueous solution, there's always water. So in this case, what's the pH? Well, is this an equilibrium situation? No. It goes to completion. So if it goes to completion, all you have to do is take the negative log of this value, because it's 1-to-1, one hydrogen ion for every molecule. So that is the hydrogen ion concentration in solution. All right, now what would interfere with the determination of this pH? Notice that the concentration here is 10 to the minus third molar. Right? What's the concentration of hydrogen ions in pure water? 10 to the minus 7th. All right, so this concentration of hydrogen ions, 10 to the minus third, is 4 orders of magnitude higher, 10,000 times more concentrated than pure water. So that's why we can say this dominates the pH. If this value got really close, say 10 to the minus 7th or even 10 to the minus 8th molar hydrochloric acid, the pH of the water would not change, because then the dominant reaction would be the self-ionization of water molecules, simply because hydrochloric acid was so dilute. It would have no impact on the pH. And that's what this problem discusses. If you say your concentration of HCl is 10 to the minus 11th, right? So that's 4 orders of magnitude less concentrated than pure water. Now, why is it 10.8? I would expect it to be 7. 1.5 times 10 to the minus 11th molar solution. Well, that's saying it's basic. Oh, it is. It is basic. Right? What's the pH of that one? 1.5 times 10 to the minus 11th. Take the log, the negative. I'm going to have to think about that one. Why would the concentration be 10 to the minus 11? It would be that way because we're favoring the base side of the reaction by saying that the concentration is this, and this is equilibrium concentration, right? This is not just what you add to the solution. If this solution is actually that value, then we are basic. So what happens with this reaction? Nitric acid in solution. Well, in this solution, nitric acid dissociates completely. It's a strong acid and produces essentially all of this. Why does this one not? Why do we take this nitrate ion and react it with water, and produce these products? Why not? Because nitric acid is a strong acid. That means nitrate ion is a weak base. It will not strip a proton from water. Right? So this reaction is, you throw it out. It doesn't happen. All right, now we're getting to the topic of what reactions actually control the pH. Because you may have competing reactions, and it may be impossible to do a pH calculation until you decide which one actually controls the pH. Because if you have competing reactions, then your only option is to combine those reactions into a single one, calculate the K value, and determine the hydrogen ion concentration from that. And you'll probably end up with the same answer as if you eliminate the reactions that don't control and focus on the one that does control. All right. So in this case, 10 to the minus 2 molar nitric acid, that's concentrated enough to say that hydrogen ions, yes. Nitrates, yes. Water, yes. HNO3, no. There's none of it left. It's a strong acid. So what controls the pH? The dissociation of nitric acid. And we just take the negative log of this concentration and you get that pH. So for strong acids, and strong bases for that matter, if the concentration is high enough, that controls the pH. So these are just steps that you would go through and They're just there for your review. I would mention, though, when we start building ice tables for acid-base equilibrium, the same, I wouldn't call it a trick, but the same approach is advisable to select your unknown value in such a way that solving for that unknown value gives you your answer, so that you don't have to make another calculation based upon that unknown. Now, it's not always possible, but in many cases it is. Choose your X wisely. Sometimes, particularly if the K value is very small, we are able to simplify the equilibrium expression derived from the ice table, and then calculate, avoiding the quadratic or even the cubic or further, unsolvable algebraic expressions. Once you get your answer, check your 5% rule and see if you have violated it. If not, you're good to go. If you violate the 5% rule, then you have two choices. Go back and do the quadratic calculation, or do successive approximations. Okay, let's look at a real-world problem here. We may not take this one to completion. I think this one probably is just to set up the problem, and then we'll do another one that goes to completion. Let's see. I'm looking at my hard copy. Let's see. Yeah, there's, okay. So we've got a 0.8 molar aqueous solution of a weak acid, hydrocyanic acid, and there's your K value for hydrocyanic dissociation. What are the major species? All right. With this value of Ka, 10 to the minus 10th, major species are not going to be hydrogen ions. Major species are going to be the undissociated acid and water. Then you say, what reactions are they going to undergo? Well, hydrogen ions and cyanide ions are not major species simply because HCN does not dissociate to a great extent. As simple as that. Okay, now we have to decide, we've got our major species. I don't need to write this on the board. Major species, hydrocyanic acid and water. All right? So hydrocyanic acid reacts with water to produce these two species, and there's your K value. Water reacts to produce these species, and there's your K value. All right? Which one is dominant? Which one is further to the right than the other? The hydrocyanic acid is further to the right because the K value is larger. Right? And it's larger by 4 orders of magnitude, which means this first equation is the dominant one, the pH controlling reaction. So that's the one we focus on, which controls the pH, hydrocyanic acid. All right, that's as far as we want to take that one, just to decide which one is controlling. Now we're actually going to solve a problem. What's the pH of a 0.5 molar aqueous solution of HF? And I mentioned earlier, remember, the halogens form acids that are strong except for HF. And here's the proof. The Ka for HF is 10 to the minus 4th, which means it's a weak acid. That doesn't explain why yet. We'll do that later. So it's back to the problem. pH of a 0.5 molar HF solution, right? What are the major species? HF and water, because HF is a weak acid, right? And then, of course, H plus and F minus are not major species because it is a weak acid. Here are the possible reactions. 10 to the minus 4th versus 10 to the minus 14th. HF controls the pH. Okay, so now we set up our table. Here's the initial condition. 0.5 molar HF. Water doesn't count, right, because it's a pure liquid. There's your hydrogen ions and your fluoride ions, and they're essentially zero. We say approximately, but for all intents and purposes, they're zero. And then we choose the X in such a way that when we solve the X, we get the hydrogen ion concentration. That's why X is here, right? Because that's associated with the hydronium, the hydrogen ion concentration. So the dissociation gives us one of each. So we have plus X here, and minus X here. 0.5 minus X, X, and X. And there's our K. So we write the equilibrium expression in terms of X. Right? Set it equal to our K value. Fill in the unknown values. And because HF does not dissociate very much, 10 to the minus 10th, we're going to say that the X in this term is much, much smaller than 0.5. And say we're approximately equal to this expression. And now we solve for X. So we say 0.5 times this term, square root of that gives us X. All right, so that is the hydrogen ion concentration for this reaction. And there's the pH. Now, are we going to do the, let me see. Yeah, we are going to do the 5% rule, just to remind you how it's done. All right, so here's our expression, and we want to calculate the K value based upon the results of our ice table. Right? So X is equal to this value. Remember from the previous slide, there's X. So there's your X, here, here, here. 0.5 minus that X is here in the denominator. Calculate that, 7.481 times 10 to the minus 4th. Is that within 5% of the true K value? So we just subtract, what's the difference? Right? Divided by this value times 100, and it's 3.9%, so we're within 5%. So that's a valid estimate. If you wanted to get closer, what would you do? Well, you take that X value and you plug it in here for this X right there. And then do the calculation again using this K and find out what the X is. And when you do that, the X should give you a percent difference of much, much less than 1. If you wanted to do that, if you want to get closer, and you didn't want to do the quadratic, that's the way to do it. A successive approximation. Okay, new topic. Percent dissociation. What do we mean by that? Well, remember when we talked about the equilibrium constant versus the equilibrium position? This is sort of analogous to that. The percent dissociation is simply a calculation which ratios the amount of your acid dissociated divided by the initial amount. So if we establish an initial concentration of our acid, and then we determine afterwards that a certain amount in molar terms is dissociated, we ratio that to the initial concentration times 100, and that's it. That's your value for percent dissociation. So what value is that? Well, if you know the percent dissociation, you can calculate the K value. And we're going to do that. But keep this in the back of your mind for now, and we'll explain it as we go. For any given weak acid, as the concentration of the acid decreases, the percent dissociation increases. It's counterintuitive. Now, that does not mean that you have more hydrogen ions. That just means that the percent of the acid that dissociated increases. So if you decrease the concentration, the initial concentration of your acid, you get a higher percentage of it dissociating. Okay, so that says to me that it's sort of related to Le Chatelier's principle. All right, so let's do a sample calculation. Determine the Ka for formic acid, HCHO2, formic acid. Formic acid is a carboxylic acid. It's an organic acid. And they always have that form. That's the carboxyl group. And this is the acidic hydrogen. So you can have anything out here. If you have an H, that's formic acid. Okay. If you have a methyl group, CH3 out here, that's acetic acid. Okay, where does formic acid get its name? Formic is derived from the Latin term for ant. You know, the little crawly things, the ants. And the reason for that is formic acid was isolated from ant bites, right? Especially a fire ant. When a fire ant bites you, it spits this stuff into the wound, and that's why it burns so bad. It's sort of a cocktail. Formic acid is a major component. There are other things in there, but so if you've ever been bitten by a fire ant, you know what formic acid feels like. All right, so let's get back to the problem here. We've established that for this solution of 8 molar formic acid, which is very concentrated, the percent dissociation is 0.47%. So what does that mean? Well, if it's 0.47%, right, it's that molar per 100. Right? So we can say that if we start off with 8 molar formic acid, then the fraction of this, 100 divided into 0.47, is 0.0047 molar. That molar, right, that's the decimal equivalent of the percentage, 0.0047. That molarity is the part of formic acid that is dissociated. All right, so we lose this fraction of 8 molar. And it shows up over here as hydrogen ions and formate ions. All right, now that we know that, we can calculate the equilibrium concentration. 7.9624 versus these two. And now we can put them into the equilibrium expression right here, right? That's squared because they're both equal, right? Divided by this, and there's our Ka for formic acid based on the percent dissociation. This is the tricky part, understanding that that fraction, you don't multiply by the percent, you multiply by the fraction equivalent to get how much of it is converted. So now that we know the Ka, we can determine the percent dissociation at some other concentration. Right? Well, first we're going to do the pH. Right? So there's the hydrogen ion concentration. So we put that into our formula, and 1.42 is the formic acid concentration, pH at that concentration. All right. So the value of Ka for 4 molar formic acid, right? We started with 8 molar. So what's the value for Ka for 4 molar? That's a trick question. K is a constant. It doesn't change, right? So it's going to be exactly the same as the value for the Ka for the 8 molar. Okay? Now, percent ionization is different. And it should be higher as the concentration decreases. All right. Oh, I think what we're going to do first, hold on a second. Yeah, first we're going to get a theoretical explanation for why the percent dissociation increases as the concentration decreases. Okay, so here are starting conditions. If this is your starting concentration of your acid, right, that little 0 there means initial. And this is your equilibrium expression, right? There it is right there. And it's the same for both concentrations. That doesn't change. What changes is the actual concentration. All right. So what is the concentration of HA if HA sub 0 is this concentration? Well, they're essentially the same, right? We showed that earlier. We were only 3.9% off. So we can say that this is actually equal to the initial concentration. And the X value is equal to the hydrogen ion concentration or the conjugate base concentration. They're equal. All right. So our expression then is 2 X's times one another divided by HA sub 0. All right. Now what happens if you start at that concentration, but you add water and add enough water so that now the new concentration is only 1/10 as strong as it was? So what would that look like in your expression up here? Okay, the new concentration here initially would be X divided by 10. And the new concentration for HA would be HA, 0 divided by 10. So now that we've stressed the system, right, well, Chatelier is going to kick in. Which way will the reaction go? Well, let's calculate Q, right? We could intuitive say, but we want to know quantitatively. So what's the Q value, right? We just say before it reaches equilibrium, where we've stressed it. And this is the new concentration for the X's here, here, and for the HA is here. Right? So we can factor out 1/10. Right? Just factor out 1/10, factor out 1/10. And what we end up with is 1/10 times this value. So what does that equal to? This value is Ka. right? So the Q is 1/10 of Ka. So what happens to, which way does the equilibrium shift if the Q is less than K? If the Q is less than K, that means the numerator is too small, the denominator is too big. And the denominator is reactants. So we shift toward the right. We shift to make more product, which means that the percent dissociation increases. You have to dissociate more of your acid to make that shift possible. Okay, that's why the percent dissociation increases when we dilute the acid. All right. Oh, there's Cody. All right. We lost somebody though. Who'd we lose? Lacey. Lacey's missing. Elizabeth probably won't be here. She told me in advance. Okay. Back to the discussion. So the pH of a 4 molar formic acid solution should be what? Well, the dissociation, percent dissociation increases, but what did we do to the hydrogen ion concentration initially? We divided it by 10, didn't we? And it's only going to shift part way. It's not going to go all the way back to the original concentration. So we've actually decreased the hydrogen ion concentration, which means the pH will increase. Okay? Right, and there it is in blue and white. Okay, now let's calculate the percent ionization of the 4 molar formic acid solution. Since we now know the K value, we calculated that earlier, we can use that K value plus our ice table to determine the new dissociation constant. Not constant, percent dissociation. Okay, so here we're starting out with 4 molar and no hydrogen and no formate, and we get a loss from this side and it shows up on that side. And here's the equilibrium situation, right? So the equilibrium setup is like this, and x is going to be very small, so we can say that 4 minus x is essentially 4, and then we solve for x. So what is x? X is the hydrogen ion concentration, but it's also the formate concentration. And the stoichiometry says the concentration of this is equal to how much of that dissociated. And that's what we need to know. So this molar concentration of formate ion divided by the original concentration of 4 times 100 is our dissociation percentage. There it is, divided by 4. And now the dissociation percent is 0.67% rather than 47, wasn't it? 48. No, 47. 0.47 was the original at 8 molar. At 4 molar, our percent dissociation is 0.67. So it has increased. All right. And what's the pH? Well, we just do the log transformation, 1.57. And compare that with the pH of the earlier solution, which was, I go back one more, 1.42. So the pH has increased. Dissociation percent is increased, and the pH is increased because the hydrogen ion concentration actually decreased. Okay. So I assume that you're thoroughly confused, so we're going to switch topics here. We're going to go back to bases now. What's a strong base? Similar definition to a strong acid. Complete dissociation would be the ultimate strong base. But a strong base is one that has an equilibrium constant that's much greater than 1. Right? So if we dissociate lithium hydroxide or sodium hydroxide, potassium hydroxide, we get a very large K value. Calcium hydroxide, like I said earlier, you get a large K value, but it's not based upon the total amount of calcium hydroxide you add to the solution. It's only based upon the amount that goes into solution. So whatever calcium hydroxide dissolves in water will dissociate to a great extent. I know it's a fine distinction, but it's important. Okay. So calculate pH of this solution of sodium hydroxide. All right, so is this an equilibrium reaction, or does it go to completion? Sodium hydroxide is such a strong base that it will go to completion, which means that all we have to do is find the pH of this solution. Sodium hydroxide dissociates 1 to 1. Right? So if we know the concentration of this one, we know the concentration of that one in molarity. So the pOH is this, and the pH would be what? 14 minus that. Okay? Simple. Strong acid, strong base calculations are easy. All right. What's the pH of this solution of calcium hydroxide? Okay. Now, there's a fly in the ointment. And the fly in the ointment is how many hydroxides are produced for each calcium hydroxide? Two. So you get 2 hydroxides for every 1 calcium hydroxide. All right, so what's the concentration of hydroxides? It's 2 times 10 to the minus 3rd molar. All right. Now you can continue. 14 minus 2.7. pH 11.3. So it is basic. But this is the type of question you would see on an exam. And one of the possible answers would be, I'll just calculate it. Let's see, log, change sign, 14, 11.0. One of the answers in a multiple choice test for this question would be 11.0. That's the answer you would get if you did not take this factor into account. 2 hydroxyls per molecule. That just illustrates the point that multiple choice tests are not necessarily easier, because they also give you the wrong answer as one of the possible choices. And if you calculate it wrong, you'll see your answer there in the selections, but it's the wrong one. All right, so let me go to the next possibility. So what would be the KB expression for this reaction, right? Say we put potassium cyanide in solution. That would be completely soluble. it would make cyanide ions. Potassium is a spectator. So the cyanide reacting with water would be the dominant reaction. Cyanide is a very strong base because it comes from a weak acid. Hydrocyanic acid is very weak. Cyanide ion is a very strong base. So we would write this expression for its reaction, and this would be the Kb. And, oh, maybe that's all there is to that one. I thought we were going to do a calculation. Sorry. We'll do one for this one. So calculate the pH of a 2 molar solution of ammonia. All right. 2 molar solution of ammonia, right, is this one. But it's a very weak base. And we're actually given the Kb for this one. So that means that most of it is going to be NH3. Right? So the pH, it will produce some hydroxyls, right? And we can use that expression to, in our ice table, to find out what the hydrogen ion concentration is, or we may just find out what the hydroxyl is and actually, okay, there's no slide for this one with the ice table. What we're saying is, I'm going to put it up here. That was an oversight. So we have this reaction, and this one, like that. Then we have initial change equilibrium. All right. So the initial concentration is what? 2 molar. Right? That one doesn't count. And this one is 0 and that one's 0. Okay? Then we get what? We get one of these for one of those. So we got some of that and some of that. Like that. Excuse me. All right. This one. All right. So now, here's the expression. That one times that one divided by this one. Okay? And we're saying that because this is a very small number, that x is going to be very small also. And we set that expression equal to the Kb, because this is a Kb reaction where we stripped a proton off of water. Then we solve for x. And x is this concentration of hydroxyls. The pOH is that, then the pH is this. 11.78 would be the concentration, would be the pH of this solution. Okay. Polyprotic acids. I mentioned this earlier. With polyprotic acids, those that have more than one proton, like sulfuric acid or phosphoric acid, which has 3 protons, each of those reactions happens in succession. Right? And then you take the conjugate base of that dissociation and it becomes the acid for the next reaction. Well, there's also a characteristic progression of Ks. The first K for the first hydrogen ion dissociation is the largest one. So if we had phosphoric acid, and it produced 1 proton plus H2PO4 minus, there would be a K. All right. Then we would take this one and it would react. And then we would take this one, and it would be the final reaction. Okay. This one is the largest number. I mean, it may be 10 to the minus something, or, you know, a small number, but it's larger than this one. And this one is larger than this one. And as a general rule, the reaction that controls the pH is the first one, in most cases. Because usually this one is several orders of magnitude larger than this one. And this one several orders larger than that one. Only in rare cases where these are comparable to one another, or within one order of magnitude of the one before, will you have a significant influence on the pH from successive dissociations. Usually the first one is the controlling one. And in phosphoric acid, that is the case. Okay. Oh, there it is. So this one is 10 to the minus 3, this one's 10 to the minus 8, and this one's 10 to the minus 13. So 5 orders of magnitude smaller here, 5 more orders of magnitude smaller here, which means basically the first reaction controls the pH. Now, these reactions, they still occur, right? And they produce various components, right? So in the final, once you've come to equilibrium, you will have some of this in solution, phosphate ion. And you'll have some of this, the hydrogen phosphate ion, or the dihydrogen phosphate ion you'll have. But you'll have more of this than this, and more of that than that, for the same reasons as pH and the hydrogen ion concentration. So the first one would be that expression, right? This one times that one divided by that one, right? That hasn't changed. And if we start off with a 1 molar solution, then the concentration of hydrogen ions will give you a pH. Oops. We thought we were good, right? But when you run the 5% rule, you find out that we missed the 5% rule, right? We exceeded it. So what do? Well, you stick that value right here that you determined, and in the previous slide, we said that it was too small to be significant. Well, as a matter of fact, it is significant. So now we put it in there as a factor, right? We stick it right in there and solve for x again. This is a successive approximation. And then we do the calculation, and we find that we're now less than 1% error with our new x value. So now that we've determined the pH based upon the first dissociation, we calculate the x. Now we do the pH. Okay, so we just take the hydrogen ions and we do our log transformation and find the pH is 1.08. Right. So what would be the equilibrium concentration of PO4 3-, the phosphate ion? So we have to go through each successive calculation to get to the bottom and find out what PO4 3- is. All right. So there's the second reaction. All right, we take the conjugate base from the first reaction, and now that's the acid for our second reaction. Right. And if we do that calculation, right, we have our new H2PO4- is this concentration. We determined that from the previous reaction. And we calculate what HPO4 2- is. because that one is going to be the acid for our third dissociation. Right, so we need to know what that is. Right, there it is, X. As it turns out, if we use that estimate, that means X is the same as it was to start with. And if we do the third one, we find out that the concentration at the end, we set up this equilibrium reaction. We find that the addition of the additional hydrogen ions, which also relates to the conjugate base. See, 6.2 times 10 to the minus 8. Let's go back. Here we go. So the Ka value for the second reaction is actually equal to X. That's what we're saying here. See, there's the X and there's the K value. So by that approximation, we've said that the X is equal to the Ka. And we didn't do the 5% rule, but trust me, for a K value this small, the 5% rule is going to be easily met. And then we use, right, we find out that the hydrogen ion concentration here is essentially equal to what it was before. There's no difference. So now we have values to set in here. The hydrogen ion concentration, there's your unknown. Here's the new K value for the third dissociation, and here's the H2PO4. Then we can solve for our unknown. And that says that the phosphate concentration is 10 to the minus 19th molar. I mean, it's vanishingly small. So when we do titrations, acid-base titrations, if we were to titrate a certain concentration of phosphoric acid with a strong base like sodium hydroxide, and we wanted to determine what's the phosphate concentration in that solution, we would titrate it with sodium hydroxide, and we would find out the total concentration of this. Now, why is that if the equilibrium is only 10 to the minus 19th molar? Because when you add base to an equilibrium solution, you're disturbing it. You're shifting the reaction to the right by consuming hydrogen ions. So we actually consume all of the hydrogen ions with our base and use that relationship to determine the phosphate. So that's a quick and dirty explanation for why you can do that, even though the concentration at equilibrium is here. They're two different situations. You're disturbing the reaction with an acid-base titration. You're really only interested in stoichiometry, not equilibrium, when you do a titration. Okay, so what do we mean by a salt? A salt is a chemical term, and it's based upon acid-base reaction. When you have a base reacted with an acid, the result is water plus salt. And we use sodium hydroxide and hydrochloric acid here simply because the salt that's produced, although it's by definition a chemical salt, is also table salt. So you can get maybe it makes the transition of thought a little easier. But in chemical terms, this salt is just the combination of the anion of the acid and the cation of the base. And then what you have left over is the hydroxyl, and the hydrogen yields water. Now this type of reaction is an Arrhenius acid-base reaction because there's a hydroxyl in your base. If you had a base over here that was not an Arrhenius, it'd be a little more complicated. But whenever you do have an Arrhenius acid and an Arrhenius base reacting, the consequence is always, the products are always a salt and water. So what does that mean for the, let's see, I was going to do net reaction here. So if you actually have sodium hydroxide in water, what do you have? So you have sodium plus hydroxyls, and then react with acid plus that. So what do you get? Right. Well, on the other side, you get sodium plus chloride plus water, correct? Right. So where are the spectators? Spectators, OH minus plus H plus yields water. That's the net ionic equation for all acid-base reactions, assuming that they're Arrhenius bases. Okay, so let's see, what else was going to be talked about here? Oh, okay. When you combine an acid and a base, can we predict the pH of the resulting solution? Suppose it's an equilibrium situation. I probably shouldn't have erased that because when you combine a strong acid with a strong base, you get both of them completely dissociated. And the result is the equilibrium of this plus that gives that. And we know if this is operating, then the pH is 7. It's neutral. All right? That's for strong acid, strong base. So if you add a salt to water that is derived from a strong acid, strong base, then your solution will be neutral. What if you add a salt that was derived from a strong base and a weak acid, such as sodium fluoride or potassium acetate, or sodium acetate for that matter? Well, what you get is a basic solution. Now, the rule of thumb is, let's see, acid, base, pH. So if this one's strong and this one's strong, this one will be neutral, 7. If this one is strong and this one is weak, then it will be less than 7, acidic. If this one is weak and this one is strong, then it will be greater than 7, basic. Now, these are the actual acid and base from which the salt is derived. All right. So an example of this one would be sodium chloride. Example of a strong acid, strong base would be ammonium chloride. Right. Weak base, strong acid. HCl would be the derived acid from here. Ammonia would be the derived base, which is weak. If it was the other way around, say we had, well, let's see, there's an example right there. right? Sodium fluoride. HF is a weak acid. Sodium hydroxide is a strong base, pH greater than 7. Now, which one are we missing? What if both of them are weak? Derived from weak. For instance, ammonium acetate. Derived from a weak acid, acetic acid, and derived from a weak base, ammonia. Then you have to compare the K values of each, acid versus base, before you can determine that. Okay, so that one doesn't fit with a rule of thumb very easily. Now, that's the quick and dirty way to determine roughly the pH of your resulting solution if you add the salt. But that's not why the solution is base versus acid. The reason, excuse me, I went wrong direction. Oops. Where is it? Yeah. Okay. So here's the reason. The temptation is to say, if your salt is derived from a strong base and a weak acid, like sodium fluoride, strong base, weak acid, that the reason that the solution is basic is because of the strong base. It's not. It's just, it's counterintuitive. It's just the other way around. So look what happens. When you have sodium and fluorine, or fluoride, which is what happens when you put them in solution, what reactions will result? Is sodium going to react with anything? No, it's not going to react with fluoride because it just dissociated. It's not going to react with water, which is the only other molecule that's in there. It won't react there. So the fluoride reacts with water. And what does it do? Weak acid makes a strong base. It pulls a proton from. All right, so if we needed to determine the pH of this solution, which reaction would we start with? We'd start with the acetate ion, or with the fluoride ion, and calculate the Kb for that reaction. So if we know the Ka for the HF or the Ka for the acetic acid, we calculate the Kb and use that for the conjugate base reaction with water. Okay. In this case, we have a weak base and a strong acid. So we should have an acidic solution. We'll use the Ka for the NH4 plus. So the NH4 plus oops, sorry. What am I thinking? There we go. That would react with water and produce the hydronium, which is the acid part, and then ammonia. And for this, we would need a Ka. Well, typically the ammonia, NH3, is quoted with a Kb because of the way it reacts with water. So we would have to take that Ka and calculate the Kb before we could use this reaction. Okay, so this is what I put this on the board a little while ago. And this is the one that takes some doing, the bottom one. the conjugate acid of a weak base, conjugate base of a weak acid, and it depends on the Ka and the Kb for the values as to determine whether it's acid or base pH. All right, so this is the rule of thumb, qualitative prediction, right? That's straight out of your book, and it's easy to use that. But if we're going to use the anion or the conjugate base for each of these acids, we need the Kb's for their anions. Right, so there we go. There's the Kb for the acetate anion. Right? And there's the Kb for the cyanide ion. Okay, so what does that mean by looking at that? The Kb for the cyanide is larger. So that means the cyanide ion is a stronger base than the acetate ion. And if we put those both in solution, the cyanide ion will control the pH, especially since the difference is 5 orders of magnitude between the two. So that means you definitely have cyanide controlling that reaction if they're both in solution at the same time. Say we put potassium acetate and potassium cyanide together. Then the control would fall to the cyanide ion. Okay, so let's use what we know to predict the arrangement of 1 molar solutions of each of these compounds from lowest to highest pH. Right? You can do this 2 different ways. You can do it the quantitative way, and I'll show you that in a minute. But the qualitative way works just as well for ordering. So what do I want to do first? I want to find the one that produces the most acidic pH and the one that produces the most basic pH. You know, tie down the ends. So, are there any compounds composed of ions from strong acid base interactions? Well, actually, I take that back. We're going to find any neutral ones first. We're going to set the center position first. Okay, so are there any that are made from strong acid, strong base interactions? They'll be neutral, right? So I see a sodium chloride in there, right? So that would make our neutral solution, and it would be right in the center, pH 7. Okay, are there any strong or moderately strong bases? That would put it on the high end, from lowest to highest pH, right? So it would be on the right-hand side, highest pH. Well, yeah, sodium hydroxide will have the highest pH, and ammonia should have the next highest pH, because I don't see any more bases. See any more bases in there? No. Sodium hydroxide and ammonia. So that gives you the highest base end. Okay. Now how about, are there any compounds of weak acid, strong base interactions? Actually, I would have gone the other way. I would have said, I would have gone to strong acids and nailed down the acid end. So HBr is a strong acid, so that would be way over to the left. I guess it's coming in a subsequent step. In the meantime, if you have weak acid, strong base interaction, that's going to be a basic solution, but not quite as basic as sodium hydroxide and ammonia. Okay. So there's a weak acid, strong base right there, sodium cyanide. So it'll be just a little bit less basic than ammonia. Are there any acids derived from halogens? Okay, now we're going to get to the strong acid side. Yes, HBr will be a strong acid, but HF is actually a weak acid. But that's okay. It's a little bit weaker acid than HBr, but it's not quite as weak as HCN. Okay, so that means that now the only thing we have left is ammonium chloride and HCN. So what are their relative positions? Well, HCl is a strong acid, so it should be acidic. And I would expect HCN to be less acidic. So ammonium chloride should be second from HBr, and HCN should be the next one. Let's see if I'm right. I think that was the assumption. So HBr, HF, HCN, and then ammonium chloride, neutral, slightly basic, more basic, very basic. So that would be the order based upon what we know qualitatively about acids, bases, and salts. Now, if we use quantitative, we need to examine the relationship of Kas and Kbs. So we use Kas for the acids, Kbs for the bases, and then we need to use both of them for salts of weak together. Okay, so HBr is a strong acid. In fact, it doesn't even have a Ka. It's so strong. Sodium hydroxide doesn't have a Kb because it's such a strong base. But in between there, we have, of course, sodium chloride is neutral. We don't even need the values for those. But if we compare the Kas, we find that the Ka for actually Ka is a misnomer for ammonium chloride, right? That's a K. It's not a Ka, right? Ammonium chloride is not an acid. It's okay for HCN and HF, but that's probably put it there because there wasn't a good place to put it anywhere else. And same thing for sodium cyanide. That's not a Kb, right? Unless you're saying Kb of the cyanide ion. Aha. And the Ka for the ammonium ion. Now that would make sense. So if we assume that, then we can put the Kas in order here and find that this is a little bit stronger Ka than the ammonium. That does make sense because the chloride ion is a spectator. Right? So we're interested in the ammonium. Right? So what I said, I was thinking out loud, set that aside. We're actually concerned with the Ka for NH4, 5.6 times 10 to the minus 10. That should be a superscript in there. I'll have to correct that. And let me take just a second to make that note. Superscripts. And subscripts need to be corrected. Okay. So now with these values, we can put them in order, right? That means this is a stronger base than that one, neutral. Then we go to the Kas for these, and we find out the order of the Kas. And this is the quantitative way to put things in order. And we get the same answer. All right. So I'm going to skip this one because this one talks about major species, but it doesn't take us to a calculation. And in the interest of time, let's go to the next one, because the next one will talk about, let's see, HF. No, it is doing it. Okay, my mistake. Well, this is, okay, which reaction controls? All right, let's go to this one, HCN. We're going to do the same process, only this one, we're actually going to go to completion, relatively speaking. Completion of the problem solution. I should put it that way. Okay, what's the pH of a 0.75 molar aqueous solution of sodium cyanide? The Ka for HCN is 6.2 times 10 to the minus 10. Now, that's valuable information, but that's not the value that we're going to use for the reaction. Why? Because it's not HCN that's reacting. It's Cn minus that's reacting. Right? What are the major species? Well, sodium and cyanide dissociate. So those are major species, plus water. Now, which ones do we consider? Well, look, sodium, we could invent a reaction of sodium and cyanide and water. So we'll do that just for argument's sake. So the cyanide ion reacts with water, produces HCN and OH. That seems valid, right? Because this is a strong base. Water and water, right? What do we say? That's always there. Sodium and water, never happen. Sodium and cyanide, never happen. Why? Because it dissociated completely to begin with, right? It's not going back. So these two reactions, throw them out. They don't count. So now we have to decide which one of these controls the pH. And we look at the K value, and this Kb is for cyanide, right? This is the Ka, 6.2 times 10 to the minus 10th, divided into 10 to the minus 14th gives you Kb for the cyanide reaction. It's 10 to the minus 5th versus 10 to the minus 14th. So the larger number wins. That means the first reaction controls the pH. Now we set up that reaction. There's your cyanide ion reacting with water, producing hydrocyanic acid and hydroxyls. If we want to calculate the pH, we need to know, in this case, the hydroxyl concentration. So we start off with 0.7 molar. We start off with virtually none of this. Why is this approximate zero? Because there is some there, right? Water dissociates, but it's virtually zero. So we lose some X here, we gain some X there, and that expression is the one we use in our solution. We find that X, the hydroxyl concentration, is 3.46 times 10 to the minus 3rd molar. Right? There's the POH, there's the pH, subtracted from 14. All right? Okay, so that is a simple solution for determining the pH of a salt derived from sodium and cyanide. All right, what determines the strength of an acid or the strength of a base? Actually, there are two competing factors. One is bond polarity, and the other is bond strength. Itchy nose. They're related, but they can be treated separately and considered competing factors. Bond polarity. What does that mean? Well, when we're talking about an acid, let's say, All right. Bond polarity. In order to make an acid, the polarity has to be toward the anion. Has to be that way. Why? Because when the hydrogen ion leaves the molecule, it has a positive charge, always. So where did the electron go? The electron went over here. So that means it's always pulling that direction. Just the strength. How hard is it pulling? Well, the more polar the bond, the stronger the pull of electrons toward the anion. And the more likely it is for the proton to leave, the easier it is for the proton to leave. That makes for a stronger acid. So the more polar the bond, the stronger the acid. All other factors being equal. Okay? The other factor that operates is bond strength. So you can measure the strength of the bond also, not just the polarity. So if the bond strength is high, the acidity is low. So in order to make a strong acid, high bond polarity is good. Low bond strength is good. All right, so let's look at what we call a homologous series, which means that the only change here is their position in the family. Right? These are all halogens. Right? So the bond strength. Well, let's look at bond polarity first. Right? So what determines bond polarity? The electronegativity of the anion. Since hydrogen's the same all the way, we can just compare the relative electronegativities of each one. And as you go up, the electronegativity increases, correct? So we should see hydrobromic acid stronger than hydroiodic acid, which it is. And hydrochloric acid should be stronger than no, the other way around. I'm sorry. We would expect bond polarity to determine the strength of these acids, but it doesn't. The reason being, it's not the polarity, but the strength. And if you measure the strength, you find that the bond strength increases as you go up. Now, the reason for that is not just the difference in electronegativity, which increases the bond strength, but it's also the size of the ion. So the iodide ion is like that, and then the bromide ion is like that, and then the chloride ion is like that, and the fluoride ion is like that. So we run into a concept called charge density. The charge density here is very low. That single charge is spread out over a large area. So the strength of attraction to the proton is very low. So that decreases the strength of the bond. Plus, the hydrogen ion's got to get as farther from the iodine ion. It's further away from the iodine. Here it's closer. Here it's closer still. Here it's very close. All right, so that's what the size of the ion and the charge density does. It pushes the cation further away and weakens the bond. So hydroiodic acid should be stronger. So I said it just opposite. Hydroiodic acid should be stronger than hydrobromic, stronger than hydrochloric, stronger than HF. In fact, HF is a weak acid because as you get that charge density very tight, close, and the hydrogen ion can be drawn in very close to the anion, the bond strength goes up so high that you can't get the proton loose easily. So I have a feeling I've confused people. But there's the hard evidence. The bond strength decreases as you go down in the family, which increases the acidity. All right, so let's get off that topic and let's talk about okay, we're coming up on 12 noon, so if you have to go, fine. I'll just keep talking and I'll finish this chapter and the next chapter. I'll just keep recording. Oxyacids. What's an oxyacid? Well, it's an acid formed from a polyatomic ion that has oxygen in it. Okay? And the trend is when you have a series of oxyacids, like let's see. That wouldn't be recognizable. Let's do it like this. ClO, ClO2, ClO3, and ClO4. Right? Chloric acid, chlorous acid, hypochlorous acid, perchloric acid. The strength of the acid increases as the number of oxygens increase. So the acid strength increases in that direction. And it's very simple. If you've got chlorine in the middle and you've got an oxygen, 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 well, let's say you have an oxygen here and a hydrogen. So this is the one that breaks loose to make your acid. If you only have, like that, right here, then you've got chlorine and oxygen, which are more electronegative than hydrogen, pulling electron density away from the hydrogen, which makes it an acidic hydrogen. It makes it want to leave. But what if you add another oxygen here? In fact, I think it's like that. Then you get that additional pull of that electronegative oxygen is pulling electron density even further away from it. And that weakens the bond further. The polarity is stronger. If you add another oxygen, right, for this one, now you've drawn more electron density away from the hydrogen, weakens the bond further, makes it a stronger acid. And then if you do that, you make it a stronger acid. Actually, a perchloric acid is a strong acid. It doesn't have a K value because it's so strong. So it's the strength of the electronegativity of the group itself, drawing electron density away from the hydrogen, plus what else? The polyatomic ion is getting bigger. So it's decreasing the electron density, making it bigger, forcing the hydrogen further away from the anion, which also weakens the bond. So that explains the trend. As you increase the number of oxygens, you increase the acidity, all other factors being equal. And this is what it looks like with actual values, the K values. Well, I take that back. Perchloric does have a K value, but it's a big one, 10 to the 7th or greater. Okay. And this same trend happens with others. I used the oxychlorides as an example because there were 4 of them. If I use sulfuric acid, there's really only 2 to deal with. Nitric, there's only 2. And you can look at if you compare the oxyacids where you only change the this anion, the halogens, then you find that the acidity increases as you go up the chart rather than down. So when you add that acid, you change the whole dynamic, you switch it. Right? So hydroiodic acid would be stronger, but hypoiodous acid is weaker. So the oxygen changes everything. And then, of course, what is this? HOCH3. That's methanol. You normally don't think of methanol as being acidic, but that proton will leave, but it just doesn't want to leave very much. 10 to the minus 15 is a very, very, very weak acid. Now, why don't we have HOF in that series? Right? That's the halogen series, right? Except for the methanol. The reason is that HOF is not stable. It completely decomposes into HF and hydrogen peroxide. So the value for HOF has no meaning. It doesn't last long enough to establish an equilibrium. Okay. Other types of compounds. Once you dissolve these in solution, what do? Well, these are known as anhydrides. An anhydride is a compound which formerly contained water in its molecular makeup, water of composition. No, water of constitution. Water of constitution. So here's an example. For SO2, it can be viewed as being derived from H2SO3. And there's the water that comes out of it. When you extract water, then you get SO2 left over. So there's your SO2. That's your anhydride. You can do the same type of manipulation for NO2 and CO2, for instance. But what happens when you put them back in the water? Well, they acquire the water molecule again from solution, right, because it's aqueous, and they become acidic, right? So that's why these are called acidic oxides or acid anhydrides, because they form acids when they rehydrate. Well, notice also that these are always oxides of nonmetals. Sulfur, nitrogen, carbon are just 3 examples. They always form acidic solutions when you put them back in, dissolve them in water. As opposed to metal oxides, right? Alkali metals or alkaline earths, oxides. When they combine with water, they form a base, right? K2O combines with H2O to form KOH, which is base. So that's why these are called basic oxides or basic anhydrides. And they always form from these metals in the oxides. Okay, now I think this is the last topic in this chapter. Yeah, we're going to touch on it. We mentioned the 2 earlier concepts of acid bases. The Arrhenius acid base concept occurs only in aqueous solution and requires that the acid have a proton and the base have a hydroxyl in its molecular structure. the Bronsted-Lowry acid base focuses on the proton only, transfer of a proton. So if the proton is donated, that's an acid. If it's accepted, that's a base. And it doesn't have to be an aqueous solution. Similarly, the Lewis concept of acid-base does not have to be aqueous solution. In fact, it is most often encountered in organic chemistry. And it focuses not on the proton, but on the electrons. So a Lewis acid is an electron pair acceptor. So let's look at that. And these, the Lewis acid base concept is umbrella for Bronsted-Lowry and Arrhenius. So it works for both of those. So let's use this one. Okay. So there will be your Lewis dot structure for hydrochloric acid. When it goes into solution, what happens? Breaks apart, right? Those are two electrons in that bond. Where do they go? They go to the chlorine. So now you have this one minus ion, and this one, right, is no longer bound, right? And the Lewis structure, there are no electrons here. So that means it has to be a +1 because it has a proton in its nucleus. So what has happened? Electron pair acceptor is the Lewis acid. So it accepted an electron pair, that's this one right here, makes it an acid. Okay? An electron pair donor, for instance, would be ammonia. There's a Lewis dot structure for ammonia. And when it reacts with water, what does it do? Well, let's draw this one like. Let's do this. It's an electron pair donor. It donates to this. So now we get this one, like that, like that, like that, like that. There is the electron pair that was donated to bond with hydrogen. So now this one is a +1 charge because that electron pair stayed here to make that, right? And this one went over here and used those electrons to form the bond. So this is the electron pair donor, the base. This is the electron pair acceptor, the acid. So that way, the Lewis model for acids and bases comports with previous models, Bronsted-Lowry and Arrhenius. Okay. Yeah, that's everything I just put on the board is right there in that table. Right, so you can look at it at your leisure. In the case of the Lewis model, the solvent doesn't even have to participate in the reaction. In fact, in many organic reactions, you don't want the solvent to participate. That's why many reactions in organic chemistry are in non-aqueous solutions. Because if the solution is aqueous, water is going to participate and mess up your reaction. So you conduct your reactions in non-aqueous solutions where the solvent does not participate. Okay, this is just a summary, acid-base equilibrium problems. We're going to get into a little bit more of this in the next chapter, so I'm not going to labor this one. We're going to stop the share. And now I'm going to, let's see, hold on a second. I want to close that one and open chapter 15. Chapter 15 is shorter than chapter 14, so we should get through that one in probably about 1 o'clock. Let's see, share the screen. Now we're into this one. Yep, there it is. All right, come on, slideshow. There we go. Okay. So chapter 15 is a continuation of chapter 14. And even though it says acid-base equilibrium, we've been talking about equilibrium the whole time. I think chapter 15 ought to be renamed. It ought to be acid-base buffers, because that's our focus for chapter 15. What is a buffer? How do you make a buffer? How do you determine the pH if you have a buffer? All right. Well, first we have to consider the concept of the common ion effect. So when you have an equilibrium established, and this would be the case for non-acid base reactions too, the common ion effect. It works for either one, for acid base or for non-acid base reactions. The shift in the equilibrium using Le Chatelier's principle is based upon the introduction of a reactant or product, or the removal of a reactant or product from, say, right. So if we establish an equilibrium here, then if you add something over here, then it shifts that way. If you add something over here, it shifts that way. We know that already. Well, when you're talking about reactions that involve ions, for instance, if you have an acid and a base, then you get your salt and water. Okay. So what would affect this reaction? Well, these are in aqueous solution. So they're like this, and that, and that, and that. And this could be like that, and that. Okay? That's assuming that BA is soluble. There are some acid-base reactions that produce insoluble BAs. So that's another topic. But in this case, what would affect the balance of this reaction? Well, what are the common ions? Right? So, and it depends on whether you've got a weak acid or weak base. I mean, if this is a strong acid, strong base, you could add B's and A's all day long and it wouldn't change a thing. But if you have this one is a weak acid, then it tends to be that. Right? Now, if you add a common ion to this reaction, A minus, if you add that one, it's going to shift the reaction back this way. Right? If you add a B plus, and this is a strong base, then you won't have any effect because the common ion occurs on both sides. See what I mean? It has to be, the ion has to be involved in the reaction. And when we say involved in the reaction, it actually has to do something. And if these are both strong, those ions don't do anything, right? Everything is dependent upon the protons and the hydroxyls. Now, I left those out. If you add hydroxyl as a common ion, produces water, then the reaction will shift that way, right? Or if you remove hydroxyl, it'll shift back this way. That also is a common ion effect. It doesn't have to just be from the acid or base, the cation anion. It can be protons and hydroxyls also. Those are common ions in an acid-base reaction. Okay. So in this reaction where we have hydrocyanic acid reacting with water produce hydronium ions plus cyanide ions, we already know that HCN is a weak acid, so CN minus is a strong base. Now what would happen if we added sodium cyanide to this reaction? What are the common ions? There's no sodium ion in there, but there are cyanide ions. So you add sodium cyanide, you're actually shifting the reaction toward reactants because you added some cyanide ion. Okay? This gets to the heart of buffers. How are buffers formed? Well, let's go definition first. A buffer in terms of chemistry, acid-base chemistry, a buffer is any solution that resists a change in pH. It doesn't fix the pH at a particular point and hold it there, but it does resist a change in pH. In other words, a buffered solution, if you add acid, it may become very slightly more acidic, but not much. Or if you add a base, it might go slightly basic, but not much. It's a very, very small change. Not what you would expect if you add pure acid to water. You get a huge change in pH. But if you add it to a buffered solution, you get a very, very, very small change in pH. To a point. We'll talk about that in a minute. Generally speaking, buffered solutions are formed from either weak acid or a weak base. That's your starting point. If you add, say, a weak acid and you add a strong base to it, then the pH will tend to increase to a point and then it'll flatten out. And when it does that, you're in the buffer zone. So let's use an example. Okay, so we have pH here, and we have added sodium hydroxide here. Okay, let's say our weak acid is acetic acid. So we have HC2H3O2. And our pH scale goes, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's high enough. Our pure acetic acid solution, say for simplicity's sake, say it's 1 molar, or even a 1/10 molar. The pH of that solution is going to be in the neighborhood of 3.5, right in here. Right? no base added. Once you start adding base, then you're neutralizing some of those protons. In other words, they're combining with the hydroxyls to make water. And your pH starts to increase. And it increases up to in this region. And then it flattens out. Almost flat. Only very slightly increased. And then it'll stay there for a while until you're almost used up hydroxyls and protons. And when you get to that point, the pH starts to go like that until it reaches a certain level, and then it goes flat again. So right in here is the equivalence point. Okay? That's when the number of hydroxyls and the number of hydrogens are exactly equal. Okay? So when does this happen? Well, I tried to draw it to scale as best I could. This happens right smack dab in the middle of the buffer zone is halfway. Okay, so when you neutralize half of those hydrogens with your base, you're in the middle of the buffer zone. Okay, that's what happens with a weak acid and a strong base. You can draw that same scenario with a weak base and a strong acid, only it starts up here and goes down the other way, right? Because if it's a weak base and you neutralize it with an acid, it starts off at a basic pH and then it goes down. So the argument's similar. Now, I think we're getting the cart again ahead of the horse here with this discussion. So I'm going to leave that for now and come back to it in a minute. Okay, so what do we have here? Well, let's look at the chemistry. Let's see. Maybe I can draw it over here. I'm still on, yeah, I'm still on scale. We have the acid plus the base yields. I'm going to have to erase some of that. Yields the salt plus water. Okay, so what's actually happening here? Well, this is predominant aqueous over here. This is actually sodium ions and hydroxyl ions. And then this is sodium ions and acetate ions. Okay. Now, how else can we write this equation? Well, if it's a weak acid, we could write it like just the acid is in equilibrium with dissociated ion plus the conjugate base. That's another way to write it. Okay, so this is going to be, what would be the equilibrium expression for this? Like that. Okay, now what does it look like? let's see. What does this look like on our curve when we hit that flat point? We had used up half of these, right, with our base. So what does that mean? That means the other half is this form, right? Because the base kicked that hydrogen off and made water out of it. And now we've got sodium acetate is equal in concentration to acetic acid. All right? So this concentration is equal to that concentration. That is the middle of the buffer zone, when that one's equal to that one. All right, so now that we have that, we can talk about buffering in terms of ratios. The ratio of this anion to that acid is the key. And both Henderson and Hasselbalch recognized that. Henderson first proposed this generic acid dissociation, right? So it'd be this making that and that. And then he wrote his equilibrium expression. And then he said, look, the hydrogen ion concentration, which can be transformed into pH, is equal to the Ka times this ratio. So he recognized, Henderson did, that ratio was all important. And if this ratio is equal HA equal to A minus, that's that divided by that is 1, correct? So when these two are equal, 1 times Ka is equal to the hydrogen ion concentration. So whenever you got these two equal, the hydrogen ion concentration is equal to the Ka. Right? So that's at that buffer point where those two are equal. Then we can say Ka is equal to the hydrogen ion concentration. Hasselbalch took it one step further. By this time, Sorensen had proposed his pH transformation. Henderson didn't know about it then, but Hasselbalch did. And he took Henderson's equation and he did the log transform to it. Okay? Okay, so Sorensen came a year after Henderson proposed his equation. And then Hasselbalch went in and took Henderson's equation and applied Sorensen's transformation to it. And this is what he got. Right? Okay, so there's your equation for Henderson. Take the negative log of both sides. What do you get? Okay, there's the negative log of the hydrogen ion concentration. Simple. How does this one work? The negative log of that expression. Well, we're going to keep the ratio together because it's so important. We don't want to mess with that ratio. So we're just going to transform this one into pH and this one into pKa. Right? Negative log of Ka is pKa. Right? So there's pKa, there's pH. And we leave this one alone because we don't know what HA and A minus are exactly. But if we do know that ratio, then we have a handle on where we are in that curve, right? Because the ratio changes as you move through that titration curve. It's only equal on that flat spot right in the middle. The other places, it's a different ratio. So the ratio is our focus, and we're going to leave the ratio alone so that we can use it in calculation. Well, Hasselbalch didn't much care. He was kind of like Sorensen. He didn't much care for negative numbers in his equations either. So how do you change a negative log to a positive log? you take this term and invert it. If you invert that term, it changes the sign of your log. Right? Go back to your algebra book or whatever and see that, and you'll see that's a legitimate transformation. So now we have the Henderson-Hasselbalch equation, pH equals pK plus the log of the ratio of the conjugate base concentration to the undissociated acid concentration. That's our Henderson-Hasselbalch equation, and that's the derivation. So, the best place for the buffer pH is on that curve where the concentration of A minus is equal to the concentration of HA. When those two concentrations are equal, the pH is equal to the pKa. And that is the best buffer position also, because it will resist a addition of acid or an addition of base. All right. So let me see. I don't want to steal my own thunder. I was looking for no, I better cover it now before we get into this problem. Okay, we don't need that anymore. We'll focus on this equation right here. If this is in a buffering situation where that concentration is equal to this concentration, then what happens, and we're at equilibrium, what happens if you add H plus or acid, right? It's a common ion, so it will have an impact. If you add this, what's going to happen? It's going to react with some of that and go this way. So what does that do to the pH? It resists a change in pH because the hydrogen ions that you added are consumed. Not all of them, but many of them are consumed. Okay, that's what happens when you add an acid. What happens if you add a base? Well, if we add a base, actually base is not a common ion here. What we have here is a coupled reaction. So if you add base, it's going to make water, right? You're going to consume hydrogen ions by this strong base, this strong conjugate base to make water. It removes hydrogens. Now what's going to happen? This is going to shift over here and make more hydrogens to replace the ones you lost. It won't replace all of them, but most of them. Right? So that's why you need a substantial amount of this and of that to resist a change in either direction. All right. So now we'll get to a buffer problem. What's the pH of a buffer solution that is 0.45 molar acetic acid and 0.85 molar sodium acetate? So what does that mean? We know what this means. That's how much acetic acid is in the solution. But this one is how much acetate ion is there. 0.85 molar. It's 1 to 1. So you've got 0.45 molar undissociated acetic acid, relatively, and 0.85 molar acetate. The Ka for acetic acid is 1.8 times 10 to the minus 5. I said earlier, I said 10 to the minus 7th, didn't I? That was wrong. It's 10 to the minus 5. Okay. So if we use the Henderson-Hasselbalch equation, all we have to do is say What is the acetate concentration? There it is right there, 0.85. What's the acid concentration? There it is right there. There it is right there. There's your Ka. You got an equation in one unknown, solve it. 5.02 pH for that buffered solution. All right. So this is an explanation like I gave you on the board just then. It's like an artist rendition. You can look at it if you want. Okay. And this is a restatement of how important that ratio is. The pH of a buffer solution is determined by the ratio. If the ratio is exactly equal, A minus to HA, then the log of 1 is what? 0, right? 10 to what power is equal to 1? 0. 0 power. That's 0. So that's why when you have this one equal to that one, pH is equal to pKa. Now, this could be a very high concentration. It could be a very low concentration. The ratio is the key. Now, there's a difference between high and low concentration. Even though the ratio is the same, if you have a low concentration of A minus and HA, what does that say about the buffering capacity? The buffering capacity of your solution is very low if the concentrations are low, even if they have equal and therefore a ratio of 1, then your buffer capacity, your buffer pH will be the same, but the capacity will be very low. So it will not absorb a lot of acid or a lot of base addition. But if you have very high concentration of A minus and HA, the ratio is correct, you're in the middle of the buffer zone, you can add a lot of acid or a lot of base and still maintain the pH. Okay, that's what we mean by buffer capacity. How much actually can you add, protons or hydroxides, and maintain the pH? And there's an expression for that. Let's see. This is what it looks like. Beta, this is the Greek letter beta, is used for buffer capacity. And it's actually refers to a change in normality produces how much change in pH. And normality is an expression of concentration of acid protons or base hydroxyls. And we use normality because it eliminates the variable of polyprotics, right? So if we said 0.5 molar H2SO4, what would the molarity of the protons be? Well, it's twice, right? You got 2 of them. So it'd be 1.0 molar protons, which is equal to 1.0 normal H2SO4. Okay, so the focus is on the protons or on the hydroxyls, depending on whether it's an acid or a base. That's why the N is used here rather than the capital M. The change in normality relative to a change in pH. That's buffer capacity. Okay, and we often say rather than protons or moles, we say equivalents. So 1 molar H plus is like 1 equivalent per liter. Which, and if it's derived from hydrochloric acid, that would be 1 molar hydrochloric. If it were derived from phosphoric acid, that would be 0.333 molar phosphoric acid. They would all produce the same number of equivalents per liter. Okay, that's all I wanted to say about that. So how do you choose a good buffer? Well, we've sort of given you a lot of clues so far. It depends on what pH you want to establish for your buffer. What you want for your buffer pH, you want the pKa of your acid to be as close to the pH of choice. Okay. So for acetic acid that has a 10 to the minus fifth, 1.8 times 10 to the minus fifth, times 10 to the minus 5 Ka. What's the pKa for that? I think it's 4.74 or something like that. 1.8 exponent 5 minus, you take the log and then change the sign. 4.74. There. That would be the ideal pH for acetic, for an acetate buffer. You have acetic acid and the anion, the salt, together with 1-to-1 ratio. Your best pH for an acetate buffer there would be 4.74. Now you can buffer it a little higher, a little lower, but you sacrifice some of your capacity by doing that. Okay, I showed you that titration curve earlier. The equivalence point is where the acid and base equivalent are equal during a titration. That's the stoichiometric point for the acid-base reaction we call equivalence. So there it is as an example. Right? So the buffer zone would be right down here. You could do a similar titration for, well, actually, this is a titration of a strong acid, strong base. You're not going to have a buffer there. You will not make a buffer with a strong acid, strong base. It's impossible. But how do you solve a problem, a buffer problem, if you have a weak acid and a strong base? Well, it's a two-step problem. And I go back to, excuse me, to that original discussion on, do we let it go to completion, or do we discuss it in terms of equilibrium? When you're talking about buffers, you do the stoichiometry first. You go to completion. Then you work the equilibrium based on the information that comes out of step one. All right, so say we have a solution made of mixing 0.1 moles of hydrocyanic acid with 0.04 moles of sodium hydroxide in 1 liter. So that means we're starting off with 0.1 molar hydrocyanic acid and 0.04 molar sodium hydroxide. Right? All right, so we go back and we ask ourselves these questions. What are the major species? Well, this is what we start with: HCN, sodium, OH, and water. What reactions are possible? Right? You can get water-water, of course. You can get HCN in water, which is, it's there. It really is there. You can get HCN and hydroxyl, right? You're adding base, right? So that's a valid reaction. Sodium and hydroxide, no. It's a strong base. The reaction is completely over here, right? So you don't get any sodium hydroxide formed from that. And sodium and water, you don't get any reaction there. So those two are out. These three are valid reactions. Which reaction controls the pH? Well, the pH is controlled by the one that, let's see, hydrocyanic acid is a weak acid. So it's not going to produce a lot of protons. Water reaction is not going to produce a lot of protons. HCN and OH is where we focus our attention in the beginning, because the hydroxyl is a very strong base, right? It comes from water. Water is a weak acid. So that's a strong base, and this is a weak acid, so this is going to be a dominant reaction in the beginning, right? This is our stoichiometry, step one, the last reaction. So this is our first reaction. This is the dominant reaction for the first step. We let go to completion. It's the stoichiometry step. So what we say is all of the hydrocyanic acid we add is consumed by whatever hydroxyls are available, right? It may not use up all of them, right? But we're going to use up all of these in our first step. And then after that first step, what do we have left over? We still have some of these, right? Probably. Let's go back. Yeah, because 0.04 molar sodium hydroxide is not enough to completely consume all of the HCN. So now let's go back here. So you still have some HCN left. Now you have some cyanide ion. You still have water, and you've got some sodium. Okay. Oh, shoot. I thought we were going to go further with that one. Okay. So we're going to take a different reaction. Now we're going to use acetic acid. So the same approach. We've got a weak acid, strong base, titration. The concentration at the beginning is 0.2 moles per liter of acetic acid and 0.03 moles molar sodium hydroxide, right? So we go through that process, major species, what are the reactions possible, cross out the stupid ones, and then we do our stoichiometry, right? This reaction 3, this one plus the hydroxyls yields that one. What does that give us? Okay. So this is the reaction that works first. The strong base will react with the donor, the acetic acid. All right. So this is what happens first. Our ICE table says the acid reacts with the hydroxyl and yields some conjugate base and water. So we start off with 0.2 molar here, 0.03 molar there, nothing here. And we're going to use up all of this because that leaves a little bit of this left over, right? So we use that up, and this gives us an equilibrium starting point of 0.17 molar acetic acid and 0.03 molar C2H3O2, the acetate ion. Now we go to equilibrium, right? So now the equilibrium that controls the pH is the acid reacting with the water and yielding the acetate ion. So our starting point now is different because we did the first step. So we're starting at a different point here, there, there. So what's going to happen? Which way is it going to go? Well, we went all the way to completion with what we had in hydroxyls. And that said that there was virtually no acid in the solution. We know that's not true, but we're doing it step at a time. So this way we don't have to calculate Q. We just say, all right, if there's none of that there, then it's going to go toward products, right? Okay, so that means we're going to lose some here, we're going to gain some there, and gain the equal amount there. So that gives us our new equilibrium expression. Now we can plug that into the equation. We're going to say that the x is very small, which it probably is, and you can calculate the 5% rule and see if it obeys. But and I encourage you to do that, just to prove it to yourself. And then we solve for the hydrogen ion concentration, which is X. We chose that correctly. And calculate the pH as 3.99. All right, that's the long way around. We can take, once we've completed the stoichiometry, we can take these values, plug them into Henderson-Hasselbalch, and calculate the pH. Same value, a lot quicker. All we have to do is find out what are these starting values here for equilibrium. Once we know those values, then Henderson-Hasselbalch works. Okay. Let's see. This is just another example, right? If you have a pH, you want to know the pH of a solution, 100 milliliters of 0.1 molar acetic acid, which has a Ka value of 1.8 times 10 to the minus fifth. So this one, we just say, okay, we're starting off with 0.1 molar acetic acid, 100 milliliters doesn't matter. And we say, okay, it's going to shift to the right. We're going to lose a little bit here, a little bit there. Do our calculations. We find out that the pH should be 2.87. What if we take that solution, now we add 50 milliliters of 0.1 molar sodium hydroxide. All right. So now the volume is important because we've added some extra volume to it. And not only that, we've added a strong base. Right? So now what we need to do, let the reaction go to completion. So what's the initial concentration of acid? It's no longer 0.1 molar. It's 0.01 moles of acetic acid divided by 0.15 liters of solution. That's why 0.0667 is our starting point for acetic acid and not 0.1. And by the same token, 0.03 molar hydroxyl because it was diluted by the solution that you added it to. So now this is our starting point for the stoichiometry. We're going to use up all the hydroxyls, and that'll leave us a little bit of acid behind, plus it'll make some acetate ion. Now, that's our starting point for the equilibrium steps. The equilibrium, we can set it up like this, and we say, all right, so what's our equilibrium situation? Well, we took this and that and made this, right? So we could set up an ice table, right? But we know what the conjugate base is, and we know what the acid is in concentration. Plug them into Henderson-Hasselbalch, and the pH is 4.73. Right? So you don't even have to set up the second ice table. You know the starting point for your equilibrium ice table, that goes into the equation. All right. So what if we have, instead of a weak acid, we use a weak base? So we want to know the pH of a solution made by mixing 100 milliliters of 0.1 molar ammonia, which has a Kb of 1.8 times 10 to the minus fifth. That's odd. It's the same number as acetic acid, only this is a Kb and not a Ka. And then 50 milliliters of 0.1 molar ammonium chloride. So that gives you this ammonia, which is the conjugate acid of the base. So there's what happens. We've got ammonia, which is reacted with water to make ammonium and hydroxyl. And we've established the concentration, the beginning concentration is 0.0667 because it's diluted from 0.1, right? Same reason as before. Ammonium is actually this concentration. And we're saying there are no hydroxyls at this point. But there's our equilibrium after stoichiometry. Okay, let's carry it out some more. So there's the Kb is this expression, right? The Kb is associated with this equation, and that's why we have to use the Kb, because we're producing hydroxyls. And then we say that X is so small that it doesn't matter. So we're actually getting rid of both of these X's, that X and that X. And solve the equation. And we find out that the POH is this value, the pH is that value. Okay? Now, can we use Henderson-Hasselbalch in this equation? The key for this one is that this is not an acid reaction. So we've got to do the acid reaction to use Henderson-Hasselbalch. Okay. So this is what the acid reaction would look like. There's the conjugate acid of our base, and there's the equilibrium concentration. There's the base. Right, this would be equivalent to the A-, this would be the HA. Now that we know those values, we can't use Henderson-Hasselbalch with a Kb. We have to have the Ka. So we take the Kb of ammonia and convert it to the Ka for ammonium. And that turns out to be 5.56 times 10 to the minus 10th. Right? And the pKa is 9.25. So we plug in the negative log or the pKa here, the ratio, and we have to get this ratio right. This is the conjugate base of that acid. That's the A-, and this is the HA. Right? So if you don't put those in the correct order, then you get the wrong answer. And then solve for the pH. 9.56 is the same as the one we got on the previous slide. So you can use Henderson-Hasselbalch for weak base calculations. You just have to go the extra step and find out what the acid conjugate base values are, plus what's the Ka for the reaction. All right. So let me see. Do we need to spend time on this one? I want to get into indicators here pretty soon. Let me see if there's any value to going through this one. Okay, this shouldn't take too long. All right. Calculate the pH of a solution made by mixing 1 liter of 0.5 molar ammonia with, that's Kb, and a half liter of 0.1 molar ammonium chloride solution. And then add 0.1 mole of HCl. All right, there's one assumption that we have to make here. Once we've calculated the concentrations of ammonia and ammonium, when you add this many moles of HCl, oh, and that's why I said it was a gas, right? The reason I want to add it as a gas is so that it dissolves in solution, but it doesn't change the volume. If you change the volume, then you've got to do a whole nother set of calculations. So that's why I changed the wording here to gas. We're going to bubble that much hydrogen chloride into the solution. Okay, so our starting concentration of ammonia is 0.5, well, there's 0.5 moles and 0.1 mole of ammonium based on this information up here. So notice that the calculations, preliminary calculations, are being done with absolute amounts. That helps us work around the volume changes. We'll calculate the concentration after we do this part. You may have, no, you haven't got that point yet. This is the same type of method that I'm using in the complex ion lab. And when you read that lab and when you look at the associated documents that help you through the calculations, you'll see that we do this similar trick, using absolute amounts first, then do the calculation for volume afterwards. Okay, so what do we got to start with? Before the reaction, we have this many moles of ammonia and this many moles of hydrogen chloride, right? There it is right there. And we have this many moles of ammonium, right? So that's where we start. After the stoichiometry, we have consumed all of the hydrogen ions and used up 1/10 of the ammonias and produced another 1/10 of ammoniums. Right? So that's before and after. That's the stoichiometry of that reaction. Now, the after situation is the beginning of our equilibrium. Right? So that's what we go to the next page. Now that we know that our after amounts are 0.4 and our total volume now is 1.5 liters, right? Because we added them together. Now, the concentration of the base, A minus, is this. The concentration of the acid, HA, is 0.133. We can use Henderson-Hasselbalch. Right? So again, we have to calculate the pKa from the pKb. We did that on a previous slide, but here it is just for, to make the story complete. Then we can plug it into our Henderson-Hasselbalch and find that the pH is 9.55. And all you have to do is just go in the lab, add those, mix those together just like that, and check the pH. It'll be 9.55. Okay. This one takes a little bit more doing. Sometimes it's good to know what is the pH at the equivalence point. Not the buffer point, but the equivalence point. So remember that when the titration curve went like this, right there, you had a pH, right? So our buffer pH is here. That's pKa. But our pH equivalence is there. That's a different value. So we're going to use what we've learned so far to calculate what is the value at equivalence. All right. So if we add 100 milliliters of 0.1 molar acetic acid, which has a Ka of this value, and you titrate it with 0.1 molars sodium hydroxide solution, right? So how many milliliters of sodium hydroxide are required? Well, for every mole of hydrogen ions here, you have the same number here. So it takes an equal volume of sodium hydroxide, 100 milliliters, doesn't it? Equal volume, right? Molarity times volume equals molarity times volume, which means the moles here equals the moles there. So that means you need 100 milliliters of sodium hydroxide solution. Simple. So the total volume is 200 milliliters. That's important. Which means that at the beginning, you're saying that before the reaction, the concentrations of both of them, because they're equal, 0.1 molar, 0.1 molar, the concentrations of both is actually 0.05 molar. When you add them together, you're saying, you know, you're saying that before the reaction starts, their concentration is 0.05. And that's why. Okay. The initial then is 0.05 and 0.05. Then we let the reaction go to completion. Now we have no acid, no base. We only have acetate ion. Okay. Now what do? Well, the acetate ion is a strong base, remember? Weak acid makes a strong base. So it is going to react with water. Now the dominant reaction is that acetate ion plus water. Right? There's no acetic acid. There are no hydroxyls in the beginning. But since they're not there, the reaction's going to the right. And we're going to lose some of this acetate ion and produce acetic acid and hydroxyl. So now we have an equilibrium situation. But we can't use the Ka for this reaction. We have to use the Kb because it's the acetate ion reacting with water, not the acetic acid dissociating. So we need the Kb, 5.6 times 10 to the minus 8. Do the calculation. Then we say, there's our expression, there's the equivalence, and we're saying, after all that, the X is actually the hydroxyl concentration. So POH subtracted from 14 gives us our pH of 8.72. So this is going to be 8.72. Okay? Now, why did we go to all that trouble? Simply put, if you have one reaction that needs to be titrated to completion, you can draw the curve, and you'll know when you get there, by that position, that tells you how many milliliters of base you added, and you can back calculate to the concentration of acid. But if you have 100 of these calculations to do, 100 of these titrations to do, and you've only got a couple of hours to do them, you want a quicker way to get there. You can't draw the curve for every one. So what you need is you need an indicator, something that will change color when you get close to that point. All right? That's why we need to know this pH, because the indicator needs to change pH within a narrow range of that pH. Okay. And the acid, right, the pKa of the acid determines what pH, at what pH the equivalence point is reached. If we're right in here, 10 to the minus 4, 5, right in there, you know, you're going to have an equivalence point of in the neighborhood of 8, a little less than 9. If you have a Ka that's larger, your equivalence point is going to happen at a lower pH. Right, so it varies. All right. And this is just what happens when you titrate a base with an acid, right? Just invert the curve. So what happens here? Well, if we do it with a pH meter and we determine quantitatively that point, that's the equivalence point. But we can't call it that if we're using a color indicator. So we have to call that something else. That's the end point. Okay, that's the end point of our reaction. And if you choose your indicator correctly, the end point and the equivalence point will be very close together because this is a logarithmic scale. So that change of just a few points of logarithm means a big change in pH. But on that curve, the indicator can be right in that range, and your values will be very good. Okay, here's an example. The first thing to recognize with an indicator is that the indicator is also undergoing a reaction. And indicators are weak acids, right? So this indicator has that hydrogen, right? And addition of base is going to consume that hydrogen and drive the reaction toward the deprotonated, the conjugate base. And that's a difference in color, right? In this case, we're using phenolphthalein. So when it's protonated, it's colorless, and when it's been deprotonated, it turns pink. Now, when does that happen? Well, the Ka is 3.9 times 10 to the minus 8, so the pKa is 9.4. And it just so happens that that value, 9.4, is the pH at which the color changes noticeably, right? Because then this is equal to that concentration. Now, there's physiology involved, right? When can the human eye detect that change? Well, the human eye is not that good. Right? You need to see a difference in concentration of about 10 to 1 in order to definitively say the color has changed. That's why when we do these titrations, we have to be very careful when we get right to the endpoint. Right? If you go past the endpoint by 1 drop, you're going to be way off in your calculations. So this pKa for the indicator needs to be close to the pH of the equivalence point for your titration. So what does that mean in terms of pKa? What it means is that the indicator is effective on a 10 to 1 ratio between plus or minus 1 pH unit. Why? Because the pKa, the pH is a log transformation, base 10, powers of 10. 1 power of 10 is 10 to 1 ratio. So plus 1 pH unit, minus 1 pH unit puts you plus or minus 1 around that pKa. Okay, and here's a description of it over here, right? Just to prove that I'm not pulling your leg. So that's what you look for. Once you know the pH of the equivalence point, then you can search for the indicator that meets the conditions, plus or minus 1 unit of pH. Fortunately, you don't have to do that calculation. There are charts, right? Once you know the pH, like for our pH is 8.7 something right in here, just go down until you find one that matches it right in here. Oh, we passed a couple of them up here. Phenolphthalein is right here, so it's kind of at the bottom end, right? It would be better if our equivalence point occurred around 9.2 or 9.3, but it still works. It's plus or minus 1. Okay, so in fact, I think that's, yep, that's the last slide, isn't it? Yeah, thick paper. All right, so that's it.